Welcome back to Scientific Discovery Hub, where we unravel the universe's greatest mysteries. Today we're diving into one of the most mind-blowing stories in modern astronomy, 3I Atlas, an interstellar comet that's leaving scientists scratching their heads. Imagine a cosmic visitor from another star system zipping through our solar system, spewing clouds of carbon dioxide instead of the icy water vapor we expect from comets. That's 3I Atlas, a blazing fast alien snowball that defies everything we thought we knew about space rock. Discovered in 2025 by NASA's Atlas telescopes, this comet didn't just stop by for a quick hello. It's barreling through our neighborhood at 58 kilometers per second, fast enough to escape the sun's gravity entirely. But here's the kicker: its chemistry is off the charts. While Earth's comets glow with water vapor, 3I Atlas exhales massive amounts of carbon dioxide, hinting at a bizarre frozen world, forged inches the depths of another star system. Could this be a clue to alien geology, or even the building blocks of life? In this video, we'll unpack why 3I Atlas is a cosmic puzzle box. First, we'll trace its hyperbolic escape velocity, and how its path proves it's truly from beyond our solar system. Then, we'll explore its carbon dioxide-powered jets, comparing its alien chemistry to familiar comets like Hale-Bopp. We'll also journey 7 billion years into the past, decoding how this ancient stardust survived galactic collisions and stellar storms. Plus, we'll uncover its galactic origins, tracing its roots to the Milky Way's mysterious thick disk, and debate whether it's a lonely outlier or part of a larger cosmic family. Think you know comets? 3I Atlas will change your mind. Along the way, we'll compare it to famous interstellar visitors like Oumuamua and Borisov, reveal how telescopes like James Webb and Hubble cracked its secrets, and ask, could objects like this seed life across the galaxy? So grab your space helmets. This is one comet that's rewriting the rules of the cosmos. Hit like, subscribe, and ring the bell for more deep dives into science's biggest WTF moments. Let's explore the universe one mystery at a time. In the vast tapestry of the cosmos, where stars are born and die in silent spectacle, a fleeting visitor arrives, a whisper from the depths of interstellar space. In the summer of 2025, humanity's gaze turns skyward as telescopes Chile's Rio Hurtado captured the first glimpse of 3I Atlas, a comet hurtling through the solar system at a blistering 58 kilometers per second. This interstellar wanderer, born inches the shadow of the Milky Way's galactic center, carried with it the imprints of a universe older than our own. Its discovery was not merely an event but a revelation, a reminder that our solar system is not an isolated island, but a node inches an infinite network of celestial highways. 3I Atlas, the third confirmed interstellar object to traverse our cosmic neighborhood, arrived with a trajectory as enigmatic as its origin. Unlike the familiar comets that circle the sun inches elliptical loops, this visitor followed a hyperbolic path, a cosmic slingshot that would fling it back into the void after a brief encounter with the sun. Its speed, far exceeding the escape velocity of the solar system, defied the gravitational pull of our star, marking it as a true interstellar traveler. Yet its journey was not just a matter of motion, it was a story encoded inches its composition. While most comets inches our system are cloaked inches water, ice, and carbon-based molecules, 3I Atlas exhaled clouds of carbon dioxide, a stark contrast to the familiar chemistry of its neighbors. This anomaly hinted at a birthplace unlike any inches our corner of the galaxy, a place where the laws of formation might differ entirely. The arrival of 3I Atlas stirred profound questions. Where had it traveled before reaching us? What ancient stellar nursery had forged it from primordial dust and gas? And why did its chemistry diverge so sharply from the comets that had shaped our own solar system's history? As astronomers pieced together its path, they uncovered a deeper truth. This comet was not just a transient guest, but a relic of an epoch when the Milky Way was young, when stars and their planetary systems were still coalescing inches chaotic dance. To study 3I Atlas was to peer into the dawn of galaxies, to trace the echoes of a cosmic symphony written inches the language of ice and gas. The story of 3I Atlas begins with its discovery on 1 July 2025, when the Asteroid Terrestrial Impact Last Alert System, ATLAS, at Rio Hurtado, detected a faint, moving point of light. At the time, the comet was 4.5 astronomical units, AU, from the Sun, hurtling inward at 61 kilometers per second, faster than any natural object observed inches our solar system. Initial calculations suggested a highly eccentric orbit, raising concerns that it might approach Earth's orbit. However, as follow-up observations from global observatories poured inches, the true nature of 3I Atlas emerged. Its trajectory was hyperbolic, a mathematical impossibility for an object bound to the Sun. This comet was not a native of the solar system. It had come from the interstellar dark, carrying the secrets of a distant stellar cradle. The distinction between asteroid and comet blurred inches the early days of observation. Some astronomers, including Alan Hale, reported no signs of a coma, the gaseous envelope that forms as a comet's ice sublimates under solar radiation. Yet by 2 July 2025, telescopes such as the Deep Random Survey X09 and the Canada-France-Hawaii Telescope T14 revealed a faint coma and a tenuous tail-like elongation. This transformation confirmed 3I Atlas as a comet, albeit one with a chemistry unlike any previously observed. While solar system comets typically release water vapor and carbon monoxide as they warm, 3I Atlas emitted copious carbon dioxide, a molecule that requires higher temperatures to sublimate. This suggested that its nucleus was either richer inches CO2 or had formed inches an environment where water was scarce. Further insights came from the James Webb Space Telescope, JWST, which detected traces of water ice, water vapor, and carbon monoxide alongside the dominant CO2. The Very Large Telescope, VLT, added another layer to the mystery, identifying cyanide gas and atomic nickel vapor elements rarely seen inches cometary emissions. These findings painted a picture of a body shaped by extreme conditions, perhaps inches a system where volatile rich materials were abundant. The comet's nucleus, though obscured by its coma, was estimated to be less than 1 kilometer inches diameter, a fragile remnant of a long-dead protoplanetary disk. The hyperbolic excess velocity of 58 kilometers per second, the speed at which 3I Atlas would escape the Sun's gravity, was critical to its classification as interstellar. For an object to achieve such a velocity, it must originate from outside the solar system, as no known gravitational interactions within our system could accelerate it to this speed. The Sun's gravity alone could not account for its trajectory. Instead, 3I Atlas had inherited its momentum from the galactic environment inches which it formed. By tracing its path backward, astronomers determined that it hailed from the Milky Way's thick disk, a region populated by ancient stars and remnants of the galaxy's earliest epochs. Yet, 3I Atlas's origin posed a paradox. While the thick disk is a repository of old stellar populations, its trajectory suggested a vertical velocity component, Watts-Ponce 18.5 kilometers per second, much higher than typical for such stars. This implied that the comet's orbit was inclined relative to the galactic plane, a tilt that marked it as a member of a rare population of objects. Such a path meant that 3I Atlas had not simply drifted aimlessly, but had been launched into interstellar space by forces unknown. Perhaps a violent collision inches its home system, or the gravitational tug of a passing star. The implications of 3I Atlas's journey extend far beyond its immediate presence inches the solar system. This comet is a fossil of the Milky Way's youth, a relic from an era when stars and planets were still forming inches turbulent nurseries. Its age, estimated at 7 to 14 billion years, places it well beyond the lifespan of our solar system, which is a mere 4.6 billion years old. To put this into perspective, 3I Atlas predates the formation of Earth, Mars, and even the asteroid belt. It is a time capsule, preserving the chemical and physical conditions of a stellar system that no longer exists. The comet's origin inches the thick disk, a region where stars are older and metal poor compared to the Sun's neighborhood, further deepens the mystery. The thick disk is a remnant of the Milky Way's earliest epochs, a time when the galaxy was smaller and denser. Stars inches this region formed inches environments, rich inches hydrogen and helium, but poor inches heavier elements, a stark contrast to the metal-rich disks of younger stars like our Sun. The fact that 3I Atlas originated here suggests that its home system was shaped by a different set of astrophysical rules. Perhaps inches a protoplanetary disk that lacked the volatile rich materials seen inches our own. The comet's chemical signature offers tantalizing clues about its birthplace. The dominance of carbon dioxide over water ice implies that 3I Atlas formed inches a region where temperatures were low enough to preserve CO2, but too high to allow water to condense into ice. This could mean that its parent star was warmer than the Sun, or that the comet originated inches a zone farther from its star than typical comets inches our system. Alternatively, the scarcity of water might reflect a lack of delivery mechanisms, such as collisions with other bodies, that brought volatiles into its orbit. Either way, 3I Atlas challenges our assumptions about the universality of comet formation. Perhaps most intriguing is the presence of cyanide and nickel vapor. These elements are typically associated with high-temperature processes, such as the decay of radioactive isotopes or the shockwaves of stellar explosions. Their detection inches a comet suggests that 3I Atlas's home system experienced extreme events, perhaps a supernova explosion or a close encounter with a massive star that infused its protoplanetary disk with exotic materials. Such an origin would align with the thick disk's history of violent stellar interactions, where stars frequently migrate and collide. The discovery of 3I Atlas also reshapes our understanding of interstellar objects. Until now, only two such visitors, 1I Oumuamua and 2I Borisov, had been identified, both originating from the solar apex, the direction inches which the Sun is moving through the galaxy. 3I Atlas, however, came from the opposite direction, a surprise that hints at a hidden abundance of interstellar objects inches the southern celestial hemisphere. This asymmetry suggests that our current surveys may be biased toward detecting objects inches certain regions of the sky, and that many more interstellar travelers may be lurking undetected. Moreover, 3I Atlas's trajectory reveals the dynamic nature of the galaxy itself. Its high vertical velocity and tilted orbit indicate that it belongs to a population of objects that move perpendicular to the galactic plane, a motion driven by the gravitational influence of the Milky Way's spiral arms, or the tidal forces of neighboring galaxies. These pathways act as cosmic highways, scattering debris from one stellar system to another. In this context, 3I Atlas is not an outlier, but a representative of a broader phenomenon, the galactic exchange of material, a process that has been quietly shaping the evolution of planetary systems for billions of years. As 3I Atlas continues its journey through the solar system, its fate is sealed by the immutable laws of physics. The hyperbolic trajectory that brought it to our doorstep ensures that it will never return, its velocity too great to be ensnared by the Sun's gravity. Yet, this escape is not a random event, but the result of precise calculations. The comet's hyperbolic excess velocity, a measure of its kinetic energy relative to the Sun, places it firmly inches the realm of interstellar objects. For a body to achieve such a velocity, it must have been accelerated by forces external to the solar system, whether through gravitational slingshots from other stars or the explosive dynamics of a dying planetary system. Understanding this escape velocity is key to unraveling 3I Atlas's origins. Just as a spacecraft requires a minimum velocity to break free from Earth's gravity, 3I Atlas needed a specific energy threshold to leave its home system. The fact that it achieved this velocity without interacting with the planets of the solar system suggests that its launch mechanism was intrinsic to its birthplace. Perhaps it was ejected during a chaotic phase of planetary formation, when gravitational tugs from giant planets hurled smaller bodies into the void. Alternatively, a passing star might have perturbed its orbit, sending it on a millennia-long journey through the interstellar medium. The study of 3I Atlas's trajectory also highlights the role of the galactic tide, the gravitational pull exerted by the Milky Way's mass on objects within it. Over millions of years, these tides can stretch and distort the orbits of interstellar objects, nudging them toward regions where they might interact with new stars. In this way, the galaxy acts as both a cradle and a conveyor belt, distributing the remnants of dead system across vast distances. For 3I Atlas, this journey culminated inches a fleeting encounter with the solar system. A momentary pause inches its endless voyage through the cosmos. As we prepare to bid farewell to this interstellar guest, we are left with questions that transcend its individual story. What other objects like 3I Atlas await discovery? Hidden inches the glare of crowded starfields, or the blind spots of our telescopes? How might future missions, such as the upcoming Large Synoptic Survey Telescope, LSST, revolutionize our ability to detect and study interstellar visitors? And what secrets will these objects reveal about the formation of planets, the spread of organic materials, and the potential for life beyond the solar system? The answers lie not just inches the data collected from 3I Atlas, but inches the broader context of our place, inches the universe. This comet is a reminder that the cosmos is a shared expanse, a web of connections that binds stars and planets. Inches an eternal dance. As we continue to track its path, we are not merely observers but participants. Inches a grander narrative, one written inches the language of ice, gas, and the relentless pull of gravity. On July 2025, the eyes of the universe turned toward a remote station, nestled inches the arid expanse of Rio Hurtado, Chile. There, the Asteroid Terrestrial Impact Last Alert System MAST telescope, a vigilant sentinel inches the night sky, detected a faint, moving point of light against the backdrop of the Milky Way. At first glance, it appeared to be just another celestial body drifting through the vastness of space. Perhaps an asteroid, perhaps a distant comet. Yet, as the data streamed inches, a realization began to take shape. This object was unlike anything previously observed within our solar system. It was moving too fast, its path too erratic, its origin too far beyond the familiar boundaries of our cosmic neighborhood. Designated temporarily as A11Pel3Z, the object quickly drew the attention of astronomers worldwide. Initial calculations revealed that it was traveling at an astonishing speed of 61 kilometers per second relative to the Sun, placing it firmly beyond the gravitational reach of our star. This meant that 3I Atlas was not bound to the solar system inches the conventional sense. It was a traveler from interstellar space, a visitor from the depths of the galaxy. As further observations refined its trajectory, it became clear that the comet would not pose a threat to Earth, as it would remain at least 1.8 astronomical units away from our planet. Still, the sheer fact of its existence stirred a profound sense of wonder among scientists and stargazers alike. What made 3I Atlas even more extraordinary was its place in inches history. It was the third confirmed interstellar object to be discovered, joining the ranks of 1I Oumuamua and 2I Borisov. While the first two had captivated the world with their mysterious shapes and trajectories, 3I Atlas carried with it a new set of enigmas. Unlike its predecessors, it exhibited active cometary behavior, with a visible coma and the telltale signs of outgassing. This suggested that it was composed of volatile ices, much like the comets that originate inches the distant reaches of our own solar system. And yet its origin remained shrouded inches mystery. Where had it come from? How had it traveled across the vastness of interstellar space to arrive at our doorstep? These questions, unanswered yet tantalizing, set the stage for a deeper exploration of the comet's nature and its significance inches the grand tapestry of the cosmos. As the first images of 3I Atlas were analyzed, its true nature began to emerge. Unlike asteroids, which are primarily composed of rock and metal, this interstellar traveler bore the unmistakable hallmarks of a comet. An icy nucleus encased inches a tenuous envelope of gas and dust. The Sun, ever the great sculptor of the solar system, played a pivotal role inches revealing the comet's secrets. As 3I Atlas ventured closer to our star, the intense heat caused its frozen core to sublimate, transforming solid ice into gaseous form. This process released a cascade of volatile compounds, lifting fine grains of dust into a luminous coma that swirled around the nucleus. The resulting glow, though faint from Earth's vantage point, hinted at the dynamic processes unfolding within the comet. Determining the exact size of 3I Atlas's nucleus, however, proved to be a challenge. The comet's coma, a diffuse cloud of gas and dust, obscured the nucleus's true dimensions, making it difficult to separate the light emitted by the solid core from the surrounding material. Observations from the Hubble Space Telescope offered some clarity, suggesting that the nucleus ranged inches size from 0.32 to 5.6 kilometers inches diameter. However, the most probable estimate placed it at less than 1 kilometer, a relatively modest size compared to the largest comets inches the solar system. Despite its small stature, the comet's chemical composition told a remarkable story. Data gathered by the James Webb Space Telescope revealed an unusual abundance of carbon dioxide, a substance typically associated with the colder regions of the outer solar system, alongside traces of water ice, water vapor, carbon monoxide, and carbonyl sulfide. This composition suggested that 3I Atlas had formed inches an environment vastly different from the one that shaped the comets of our own planetary neighborhood. Further observations by the Very Large Telescope added another layer of intrigue. The instrument detected the presence of cyanide gas and atomic nickel vapor, substances commonly found inches the comas of solar system comets, but never before observed inches an interstellar visitor. These findings hinted at a complex internal structure, possibly the result of prolonged exposure to the harsh conditions of deep space. Unlike the comets that originate inches the Kuiper Belt or the distant Oort cloud, 3I Atlas had spent eons traversing the void between stars, carrying with it the remnants of a long-lost stellar nursery. Its passage through the inner solar system was, inches many ways, a fleeting moment inches its cosmic journey, a brief encounter with a sun that was not its own. The path of 3I Atlas through the solar system is a testament to the vastness of interstellar space and the forces that govern the motion of celestial bodies. Tracing its trajectory, astronomers determined that the comet entered the inner solar system on a hyperbolic orbit, meaning it would not be captured by the sun's gravity, but would instead follow a swift, open-ended path before vanishing once more into the cosmic abyss. With a hyperbolic excess velocity of 58 kilometers per second, 3I Atlas was moving at a speed that exceeded the solar system's gravitational escape threshold, ensuring that it would not return. This velocity alone was enough to confirm its extraterrestrial origin, as no object born within the solar system could have achieved such speed without external influences. The only plausible explanation was that 3I Atlas had been hurled from its home system by the gravitational tides of a distant star, or the violent collapse of a planetary system. The comet's closest approach to the Sun occurred on 29 October 2025, when it reached a distance of 1.36 astronomical units between the orbits of Earth and Mars. At this point, the full force of the Sun's radiation would act upon its fragile nucleus, accelerating the sublimation of its ices and intensifying its cometary activity. Yet despite the dramatic transformation it would undergo, 3I Atlas would remain a solitary traveler, untouched by the gravitational pull of any planet. Its trajectory was such that it would not come closer than 1.8 astronomical units to Earth, a safe distance that ensured it posed no risk to our world. Instead, it would continue its journey outward, eventually disappearing from view as it crossed the boundary between the solar system and the interstellar void. What made 3I Atlas's arrival even more remarkable was its point of origin. By tracing its path backward through space, astronomers determined that it had entered the solar system from the direction of the constellation Sagittarius, near the galactic center. This region, teeming with ancient stars and remnants of stellar evolution, suggested that 3I Atlas hailed from the Milky Way's thick disk, a galactic structure composed of older stars with lower metallicities. If this assessment proved correct, then 3I Atlas could be at least 7 billion years old, predating the formation of the solar system itself. Such an age would make it one of the oldest known comets inches the universe, a relic of an era when the galaxy was young and the stars were still forging themselves from primordial gas clouds. To witness the passage of such an ancient traveler was to glimpse a fragment of cosmic history, a whisper from a time when the universe was inches its infancy. The journey of 3i Atlas is not just a tale of motion through the void, but a story of origin and destiny. Its hyperbolic trajectory, defined by the laws of orbital mechanics, is a direct consequence of its interstellar birthright. The velocity at which it moves, 58 kilometers per second, exceeds the solar system's escape velocity, a critical threshold that ensures it will not be bound to the sun's gravitational embrace. This speed is not arbitrary. It is the product of a cosmic event that propelled the comet from its native star system eons ago. Whether it was ejected by the gravitational dance of a binary star, the violent upheaval of a planetary collision, or the slow erosion of a distant debris field, the forces that set 3i Atlas on its current course remain shrouded in mystery. Yet its velocity alone does not fully explain its significance. The fact that it has not been captured by the gravitational influence of any planets speaks volumes about its resilience and isolation. Unlike the comets of the solar system, which are often perturbed by the gravitational tides of giant planets, 3i Atlas has followed an undisturbed path through the interstellar medium. This suggests that it has spent the vast majority of its existence inches the cold, dark expanse between stars, shielded from the disruptive forces that shape the fates of objects within planetary systems. It is a wanderer that has traversed the galactic web for billions of years, untouched by the hands of any celestial architect. Its ancient age, estimated to be at least 7 billion years, places 3i Atlas inches a unique position, inches the timeline of cosmic history. If it indeed hails from the Milky Way's thick disk, a region populated by some of the galaxy's oldest stars, then it may have formed inches an environment vastly different from the one that gave rise to the solar system. The chemical composition of 3i Atlas, rich inches carbon dioxide, and bearing traces of volatile compounds, hints at a formation process distinct from that of the comets we know. Perhaps it was born inches a region where the temperature and density of interstellar material favored the condensation of such substances, or perhaps its parent star system lacked the heavy elements that characterize the inner solar system. Either way, 3i Atlas carries with it the imprint of a long-lost stellar nursery, a record of the conditions that shaped its creation. As it continues on its inexorable path, 3i Atlas serves as a reminder of the dynamic nature of the cosmos. It is not merely an object inches motion, it is a messenger from the past, a relic of an era when the universe was young and the stars were still forming. Its presence inches the solar system is a fleeting encounter, a brief glimpse into the vast and unseen realms of interstellar space. And yet, even inches its solitude, it offers us a window into the broader history of the galaxy, a testament to the ceaseless exchange of matter and energy that connects the stars across the vast cosmic sea. In the vast tapestry of the cosmos, where galaxies swirl inches silent symphonies and stars are born from the remnants of ancient explosions, a solitary traveler arrives, a comet not of our solar system, but a wanderer from another corner of the Milky Way. 3i Atlas, the third confirmed interstellar object to traverse our celestial neighborhood, glides through the vacuum of space with a purpose as enigmatic as the void itself. Discovered inches the summer of 2025 by the Atlas telescope inches Chile. Unlike the familiar comets that dance through the inner solar system, trailing water vapor and ancient dust, 3i Atlas exhales a breath of carbon dioxide, a stark contrast that defies expectations. Its journey is not merely a passage through space but a whisper from the distant past, a relic older than the solar system itself. As scientists peer through the lenses of the Hubble and James Webb space telescopes, they unravel a puzzle. Why does this comet, born inches the cold expanse of another star's realm, carry such a different chemical signature? What does its presence tell us about the diversity of planetary systems, the chemistry of life's precursors, and the ancient history of our galaxy? In the quiet hum of the cosmos, 3i Atlas stands as a testament to the boundless variety of the universe, inviting humanity to gaze beyond its own backyard and ponder the infinite possibilities of existence. When the James Webb Space Telescope first turned its infrared eyes toward 3i Atlas, It revealed a composition unlike anything seen inches the solar system. While comets native to our region are predominantly icy bodies, their activity driven by the sublimation of water and carbon monoxide as they approach the Sun. 3I Atlas is dominated by carbon dioxide. The Hubble Space Telescope's observations corroborated this anomaly, showing a coma, a tenuous envelope of gas and dust, where CO2 molecules reign supreme. The Sun's warmth, even at a distance of 1.36 astronomical units, AU, triggers a cascade of sublimation. The comet's nucleus, a frozen heart of volatiles, releases plumes of CO2 gas, which then lift dust grains into space, forming the glowing coma that marks its passage. This divergence from the norm raises profound questions about the comet's origins. In the solar system, comets originate from the Kuiper belt and the distant Oort cloud, reservoirs of icy bodies shaped by the gravitational tugs of the giant planets. These regions are rich inches water ice, their chemistry molded by the conditions of the early solar system. Yet 3I Atlas's ES's K2-dominated Coma suggests a different birthplace, one where water was scarce and carbon dioxide, a more volatile compound, played the dominant role. Such a scenario implies that the comet formed inches a protoplanetary disk, far from its parent star, where temperatures were low enough for CO2 to condense into ice. This places 3I Atlas's origin inches a frigid, outer zone of its home system, perhaps analogous to the Kuiper belt, but inches a stellar environment with a distinct chemical fingerprint. The implications are staggering. The presence of CO2 inches, such abundance, indicates that the comet's parent system may have lacked a water-rich asteroids and icy moons common inches our own solar system. Instead, it hints at a planetary architecture shaped by different physical and chemical processes. Could such systems be more common than we imagine? Their histories hidden behind the veil of interstellar distances? Or is 3I Atlas an outlier, a singular artifact of a long-lost stellar nursery? For now, the comet remains a cryptic envoy, its CO2-rich tale a message from a world we have yet to fully understand. The study of 3I Atlas forces astronomers to confront a fundamental truth. The universe is not a monolith of uniformity, but a mosaic of variation. Every interstellar object that crosses our path is a fragment of a story written inches the language of chemistry, gravity, and time. The dominance of carbon dioxide inches 3I Atlas's Coma is not merely a curiosity, it is a window into the diversity of planetary formation. If this comet formed inches a cold, CO2-rich region of its parent system, then it suggests that some stars may lack the water-rich environments that shaped the icy bodies of the solar system. Such disparities challenge the assumption that all planetary systems follow similar developmental paths. Consider the implications for astrobiology. Water is often hailed as life's essential ingredient. Yet the prevalence of CO2 inches 3I Atlas invites speculation about alternative biochemistries. Could carbon dioxide serve as a solvent inches alien worlds? Might it act as a precursor to organic molecules inches ways we have yet to discover? While Earth's biosphere thrives on water, the cosmos may harbor ecosystems where CO2 plays a central role, much like methane does on Titan. The comet's journey, therefore, is not just a tale of icy debris, but a reminder that life, if it exists elsewhere, may be as varied as the stars themselves. Furthermore, 3I Atlas's composition offers clues about the migration of materials inches its home system. The presence of trace amounts of water ice and carbon monoxide, alongside the copious CO2, suggests a complex history of mixing and processing. Perhaps the comet's nucleus is a layered archive, preserving the chemical signatures of different epochs inches its parent system's evolution. If so, it becomes a Rosetta Stone for understanding the dynamics of protoplanetary disks, where collisions and gravitational interactions sculpt the raw ingredients of planets. Yet the most tantalizing question remains: how many other interstellar objects like 3I Atlas exist, their journeys obscured by the vastness of space? The comet's southern origin, a surprise to astronomers who expected most interstellar visitors to hail from the direction of the sun's motion, hints at biases inches our current detection capabilities. Telescopes inches the northern hemisphere, where most major observatories are located, may have missed countless southern hemisphere interlopers. 3I Atlas's discovery, is thus a call to action, to expand our gaze beyond familiar horizons and recognize that the universe's richness lies inches its hidden corners. If 3i Atlas is a messenger from another star, its age is a measure of the antiquity of its journey. While the solar system is young by cosmic standards, 4.6 billion years old, the comet's origins stretch far beyond this timescale. Tracing its trajectory reveals a path originating from the Milky Way's thick disk, a region populated by some of the galaxy's oldest stars. These stars, forged inches the primordial fire of the universe, drift through the galactic plane inches orbits tilted relative to the younger thin disk where our sun resides. By analyzing 3i Atlas's velocity components, scientists have deduced that it hails from a stellar population billions of years senior to our own. Estimates place the comet's age between 7.6 and 14 billion years, making it potentially twice as old as the solar system. This staggering antiquity transforms 3i Atlas from a mere interstellar visitor into a relic of the early universe. To comprehend its age is to grasp the immense scale of cosmic time. While humans have walked the Earth for a mere blink of geological time, this comet has traversed the galaxy for eons, surviving the gravitational tides of stars and the explosive births of nebulae. Its survival is a testament to the resilience of matter inches the void, a reminder that the universe is not a static canvas, but a living, evolving entity. The methods used to determine 3i Atlas's age, comparing its velocity to the motions of thick disk stars and modeling its orbital path, are as much a study inches patience as they are inches precision. Each calculation, each observation, peels back another layer of the comet's history, revealing a story written inches the movements of galaxies. Yet even with these insights, mysteries remain. How did a body so ancient endure the hazards of interstellar travel? What cosmic events shaped its journey? And what other relics of the past await discovery inches the dark expanse between the stars? As 3i Atlas continues its flight, its legacy grows, not just as a scientific curiosity, but as a symbol of humanity's quest to understand the universe. In its silent passage, we find a reflection of our own yearning to explore, to question, and to connect with the vast, unknowable depths of space. The comet's story is far from over. It is a chapter inches a larger narrative, one that stretches across time and space, inviting us to imagine the infinite possibilities that lie beyond the familiar. This script expands the original segment into a contemplative narrative, weaving scientific detail with cosmic wonder. Each section builds upon the last, maintaining a flow that invites readers to ponder the universe's grandeur. The structure adheres to the required framework, while ensuring depth and engagement. On a crisp summer night, inches 2025, under the vast, star-dappled skies of Chile's Atacama Desert, the Asteroid Terrestrial Impact Last Alert System, ATLAS, telescope, captured a fleeting flicker of light. What seemed at first a faint smudge against the backdrop of the Milky Way soon revealed itself as a visitor from beyond the stars. This was 3i Atlas, a comet born inches the crucible of a distant stellar nursery, now traversing the inner solar system at a blistering 58 kilometers per second, a speed so great it defies the gravitational embrace of our sun. As it hurtles along a hyperbolic trajectory, the comet's path arcs outward, destined never to return, yet inches its brief passage. It carries whispers of a cosmos older than our own. Discovered on 1 July 2025, this interstellar traveler is the third such object ever detected inches human history, joining the enigmatic ranks of 1i Oumuamua and 2i Borisov. But unlike its predecessors, 3i Atlas is not merely a transient guest. It is a relic of the Milky Way's ancient past, a stardust time capsule forged inches the thick disk of our galaxy. Its arrival stirs profound questions. What secrets does it hold about the birth of stars, the evolution of planetary systems, and the raw materials that might one day seed life elsewhere? As it glides silently through the void, 3i Atlas becomes a mirror to humanity's curiosity, reflecting our longing to touch the infinite and understand our place inches the cosmic tapestry. The story of 3i Atlas begins with its hyperbolic trajectory, a path so elongated Unlike comets native to our solar system, which trace elliptical orbits and periodically return, this interloper arrives from interstellar space, with a velocity far exceeding the escape speed of the solar system. At 58 kilometers per second, its speed is so immense that even if it had passed near Jupiter or Saturn, the gas giant's gravity could not have accelerated it to such velocities. Instead, this comet was born inches the cold expanse of another star system, ejected by gravitational tides or collisions, and flung into the interstellar abyss. The Hubble Space Telescope, with its eagle-eyed precision, has revealed the comet's nucleus to be a modest world, likely less than a kilometer inches diameter, cloaked inches a coma of gas and dust. The James Webb Space Telescope, JWST, peering into the infrared, has uncovered a chemical profile unlike anything inches our solar system. A rich reservoir of carbon dioxide, traces of water ice and carbon monoxide, and even cyanide gas and atomic nickel vapor. These elements suggest a formation environment far removed from the solar nebula's conditions, hinting at a home system where volatile chemistry and extreme temperatures sculpted its icy heart. The comet's journey toward perihelion, the point of closest approach to the Sun, offers a glimpse into its interaction with our star. On 29 October 2025, it will pass 1.36 astronomical units, AU, from the Sun, a distance placing it between Earth and Mars. Though not a threat to our planet, this proximity ignites the comet's activity. Solar radiation sublimates its frozen nucleus, releasing plumes of gas and dust that form a glowing coma and a faint tail. Yet the comet's faintness, peaking at magnitude 11.7, makes it a challenge to observe. Even from Mars, where orbiters might catch a fleeting view, it remains a ghostly apparition. The Very Large Telescope, VLT, and other ground-based instruments have played a critical role inches tracking its path, revealing that its trajectory originates from the direction of Sagittarius, near the galactic center. This alignment places 3I Atlas inches a unique category. A comet born inches the Milky Way's thick disk, a region teeming with ancient stars, and the remnants of the galaxy's earliest epochs. To fathom the age of 3I Atlas is to grapple with the staggering timescales of the cosmos. While Earth's oldest rocks are a mere 4.4 billion years old, this comet predates our solar system by nearly 3 billion years. Statistical models, analyzing its velocity components and galactic origin, estimate its age at 7.6 to 14 billion years, a span encompassing the Milky Way's violent youth. During this eon, 3I Atlas has traversed a cosmic highway littered with hazards, supernova explosions that hurled shockwaves through interstellar clouds, galactic collisions that disrupted stellar neighborhoods, and stellar winds that sculpted its trajectory. Yet it endures, a testament to the resilience of matter inches the void. This longevity raises profound questions about its origins and the processes that shaped it. The thick disk of the Milky Way, where 3I Atlas emerged, is a realm of old stars, many formed inches the galaxy's first billion years. These stars, enriched with heavier elements from successive generations of dying stars, provide clues about the comet's chemical signature. Why does it contain such high levels of carbon dioxide? Could this reflect the atmospheric composition of its parent star system, or the temperature and pressure conditions of its birthplace? And what of the cyanide and nickel vapor molecules and metals that might hint at interactions with stellar radiation? If 3I Atlas preserves fragments of its primordial material, it could offer a direct sample of the building blocks of worlds inches a different corner of the galaxy. Moreover, its survival over billions of years challenges assumptions about the fragility of comets. In our solar system, comets from the Oort cloud, reservoirs of icy bodies at the edge of the Sun's influence, are typically short-lived, disintegrating after a few thousand years of solar exposure. Yet 3I Atlas, having traveled across interstellar space, must have endured harsher conditions, cosmic rays, gravitational slingshots from rogue stars, and prolonged periods inches the frigid dark. How did it retain its structure and activity? Does its nucleus harbor a unique composition or internal structure that shields it from destruction? Answering these questions could redefine our understanding of how comets form and evolve, not just inches our solar system, but across the galaxy. Perhaps most tantalizing, is the possibility that 3I Atlas carries organic molecules, complex compounds that might have seeded life on Earth. Comets inches our solar system are known to contain amino acids, the building blocks of proteins, delivered during the late heavy bombardment. If 3I Atlas shares this heritage, it could be a cosmic courier of life's ingredients, hinting that the seeds of biology might be scattered throughout the galaxy. Yet the comet's alien chemistry complicates this hypothesis. Its abundance of carbon dioxide and cyanide suggests a different evolutionary path, one shaped by a stellar environment distinct from our own. Did it form inches a system with a dying red giant? Or was it born inches a nebula where carbon-rich dust dominated? The answers lie buried inches its icy heart, waiting to be unraveled. But age alone is not the full story of 3I Atlas. To understand its journey, we must retrace its steps across the Milky Way. Its origin lies not inches the familiar spiral arms of our galaxy, but inches the thick disk, a denser, older region where stars migrate inches chaotic orbits. This distinction is crucial. While thin disk stars, like our Sun, trace orderly paths inches the galactic plane, thick disk stars move inches inclined trajectories, often intersecting the plane at steep angles. The comet's vertical velocity component, measured at 18.5 kilometers per second, confirms this tilted orbit, aligning it with a population of stars billions of years old. Yet this origin is as much a puzzle as it is a revelation. Why did 3I Atlas emerge from the southern celestial hemisphere, a direction opposite to the solar apex? The point inches the sky toward which the sun is moving. Previous interstellar visitors, such as Oumuamua and Borisov, were predicted to arrive from the solar apex. A bias rooted inches the orientation of our telescopes and the distribution of stars. 3I Atlas's southern origin defies these expectations, suggesting either an observational blind spot or a hidden abundance of interstellar objects inches this region. If the latter is true, it implies that our solar system is a crossroads for galactic travelers, a hub where the paths of countless comets and asteroids converge. To unravel this mystery, astronomers are mapping the comet's trajectory backward through time, plotting its motion against the galactic gravitational field. The results point to a birthplace inches the Sagittarius arm, near the galactic center, a region of intense star formation and violent dynamic. Yet the exact stellar system that birthed 3I Atlas remains unknown. Was it ejected by a binary star system inches a gravitational tango, or did it form inches a protoplanetary disk disrupted by a nearby supernova? These questions lead us to the next chapter, inches the comet's story, a quest to pinpoint its galactic cradle and uncover the forces that launched it on its eternal voyage. This expanded script weaves scientific detail with poetic reflection, adhering to the structure and tone requested. Each section transitions smoothly, balancing technical accuracy with cosmic wonder, while inviting readers to ponder the universe's grandeur. In the vast, uncharted expanse of the cosmos, where the light of distant stars weaves through the tapestry of the Milky Way, a silent traveler emerged on 1 July 2025, discovered by the Asteroid Terrestrial Impact Last Alert System Atlas, Station Inches Rio Hurtado, Chile. The object, now known as 3I Atlas, or C2025N1 Atlas, marked itself as a messenger from beyond our solar system. Its arrival was not a sudden spectacle, but a quiet revelation, a whisper from the depths of interstellar space. As it glided through the inner solar system at an astonishing speed of 61 kilometers per second, its trajectory defied the familiar dance of planetary orbits. Instead, it followed a hyperbolic path, a cosmic arrow aimed directly toward the sun, destined to swing past our star before vanishing into the void once more. This comet, with its icy nucleus cloaked inches a shroud of gas and dust, carried secrets older than the solar system itself. Its journey spanned eons, originating from the heart of the Milky Way's thick disk, a region where ancient stars, forged inches the galaxy's turbulent youth, drift through time. To witness 3I Atlas was to glimpse a fragment of the universe's primordial past, a relic from an era when the cosmos was young and chaotic. Yet for all its grandeur, the comet remained elusive. its faint glow barely perceptible even to the most advanced telescopes. It posed no threat to Earth, its closest approach remaining safely distant at 1.8 astronomical units. But its presence stirred profound questions. What forces birthed such an object? How did it escape the gravitational grip of its home star? And what does its arrival reveal about the hidden architecture of our galaxy? As scientists turned their instruments toward 3I Atlas, they embarked on a quest to decode the story etched into its frozen core. Each observation, each spectral signature, unraveled threads of a narrative spanning billions of years. This was not merely the discovery of a comet, it was an invitation to reimagine the cosmos as a dynamic, interconnected web of celestial wanderers. In the quiet hum of 3I Atlas's passage, humanity caught a fleeting glimpse of its own place inches the universe, a brief luminous spark amid the eternal dark. The first clues to 3I Atlas's origins emerged from its motion. At the moment of discovery, the comet was hurtling through the inner solar system at a velocity far exceeding that of any native object. Its hyperbolic trajectory, defined by a steep angle relative to the plane of the solar system, betrayed its interstellar nature. Unlike the elliptical paths of asteroids and comets bound to the Sun, 3I Atlas's orbit was unbound, a cosmic trajectory that would carry it back to the fringes of the galaxy after its brief encounter with our star. The comet's hyperbolic excess velocity, measured at 58 kilometers per second, placed it among the fastest moving objects ever observed. For context, this speed is nearly twice that of the solar system's escape velocity at the comet's point of entry, meaning 3I Atlas had no intention of lingering inches our neighborhood. The discovery process itself was a testament to the vigilance of modern astronomy. Initially catalogued as A11PEL3Z, the object's rapid movement across the sky, traversing the constellations Serpens Cauda and Sagittarius, caught the attention of the Atlas survey. Early observations were ambiguous, as the comet's faintness and proximity to the galactic center's dense starfields obscured its true nature. However, follow-up data from the Zwicky Transient Facility, ZTF, and the Very Large Telescope, VLT, quickly revealed its interstellar provenance. By analyzing the comet's orbital elements, astronomers traced its path backward through time, pinpointing its origin inches the direction of Sagittarius, near the galactic center. This location aligned with the thick disk, a region of the Milky Way populated by some of its oldest stars. What set 3I Atlas apart from its interstellar predecessors, 1I Oumuamua and 2I Borisov, was its chemical fingerprint. Spectroscopic analysis conducted by the James Webb Space Telescope, JWST, and the Hubble Space Telescope unveiled a composition unlike any seen inches the solar system. The comet's nucleus, though obscured by a coma of gas and dust, emitted copious amounts of carbon dioxide, an anomaly compared to the water-dominated outgassing of native comets. Additionally, trace amounts of water ice, carbon monoxide, and carbonyl sulfide hinted at a formation environment distinct from the Kuiper belt or the Oort cloud. The detection of cyanide gas and atomic nickel vapor further deepened the mystery, suggesting processes that might have occurred inches the vicinity of a dying star or a protoplanetary disk rich inches volatile compounds. These findings sparked debates among planetary scientists. Could 3I Atlas have formed inches the same way as comets inches the solar system? Or did its chemistry reflect a different set of astrophysical conditions? The answer lay inches the comet's age. By modeling its velocity vector inches the galactic coordinate system, researchers calculated that 3I Atlas had entered the solar system from a direction perpendicular to the Sun's motion through the Milky Way. This trajectory, combined with its high vertical velocity component, Watts-months 18.5 kilometers per second, indicated that the comet belonged to the thick disk population, a group of stars and objects that migrated from the galactic bulge during the Milky Way's early epochs. Studies published in Nature and the Astrophysical Journal estimated 3I Atlas's age at 7 to 14 billion years, placing it inches an era when the galaxy was still coalescing from primordial clouds of gas and dust. The discovery of 3I Atlas challenged long-held assumptions about the distribution of interstellar objects. Previous visitors to the solar system, 1I Oumuamua and 2I Borisov, hailed from the galactic halo, a sparse, spherical region surrounding the Milky Way's disk, Their trajectories suggested origins inches younger, dynamically active star-forming regions. In contrast, 3I Atlas's path pointed to the thick disk, a relic of the galaxy's turbulent infancy. This distinction was profound. The thick disk, composed of stars up to 10 billion years old, was once believed to be a graveyard of dead worlds. Yet here was evidence that it harbored active, volatile-rich bodies capable of surviving the galaxy's violent history. The implications extended beyond mere origins. The thick disk's high metallicity, its abundance of elements heavier than helium, hinted at a formation environment vastly different from the solar system's own birthplace. While our Sun emerged from a relatively calm molecular cloud, 3I Atlas's parent star likely formed inches a denser, more chaotic nebula, where supernovae and stellar collisions shaped the chemistry of its protoplanetary disk. The comet's carbon dioxide-rich composition could be a remnant of such extreme conditions, preserved for eons as it drifted through the galaxy. This revelation forced astronomers to reconsider the mechanisms by which interstellar objects escape their host systems, unlike the gentle gravitational nudges that eject comets from the Oort cloud. 3I Atlas's ejection required a more violent event, a close encounter with a massive star, or a binary companion, perhaps, or the tidal disruption of a protoplanetary disk during a galactic merger. Such scenarios were not uncommon. Inches, the thick disk's tumultuous past, where stellar densities were higher and gravitational interactions more frequent. If 3I Atlas was a typical product of this environment, then the Milky Way's thick disk might be a reservoir of interstellar wanderers, their numbers dwarfing those from the halo. Moreover, the comet's age raised questions about the longevity of volatile rich bodies inches the galaxy. With an estimated lifespan of 7 to 14 billion years, 3I Atlas had survived countless encounters with stars and nebulae. Its icy core enduring radiation, cosmic rays, and micrometeoroid impacts. This resilience suggested that interstellar comets might be more common than previously thought. Their volatile materials shielded by layers of refractory dust, or by the sheer cold of deep space. If so, the Milky Way's dark expanses could be teeming with such travelers, each carrying fragments of their homeworld's chemistry and history. Yet for all its ancient wisdom, 3I Atlas's journey was not without peril. Its hyperbolic trajectory, while ensuring a swift departure from the solar system, also meant that it had never truly belonged here. Unlike comets captured by the sun's gravity, which orbit for millennia before fading into obscurity, 3I Atlas was a transient guest. Its fate sealed the moment it crossed the heliopause. But how had it avoided becoming ensnared inches? Another star system. How had it endured the gravitational tides of the galaxy for billions of years, evading capture by the dense star clusters and molecular clouds that populate the thick disk? The answer, perhaps, lies inches the delicate balance of velocity and trajectory. 3I Atlas's hyperbolic excess velocity, its escape velocity relative to the Sun, was not random but a product of its ejection mechanism. If it had formed inches a binary star system, for instance, a close encounter with a companion star could have imparted the energy needed to fling it into interstellar space. Alternatively, a supernova explosion inches its vicinity might have scattered its parent disk, hurling icy bodies outward like shrapnel. Either scenario would explain the comet's extraordinary speed and its ability to resist the gravitational pull of other stars. Yet even this explanation left gaps. Why had 3I Atlas remained so pristine over eons, its chemistry untouched by the rigors of deep space? And what of the other interstellar objects yet to be discovered? If 3I Atlas was a mere whisper from the galaxy's past, what symphony of wanderers lay hidden inches the cosmic dark, waiting to be found? As the comet faded from view, its legacy lingered, a reminder that the universe is not a static realm, but a living, breathing entity, where the echoes of ancient collisions and starbursts still shape the present. 3I Atlas had not simply passed through the solar system, it had rewritten the rules of cosmic exploration, inviting humanity to look not just outward, but inward to the hearts of galaxies, to the birthplaces of stars, and to the infinite corridors of time. Beyond the icy heart of 3I Atlas lies a symphony of chemistry, a silent, frozen orchestra of molecules that hums with the secrets of distant stellar nurseries and ancient cosmic storms. This comet, a visitor from the farthest reaches of the Milky Way, is not merely a transient guest into our solar system. It is a repository of primordial materials, forged into the crucibles of dying stars and the frigid voids between them, while its most striking feature is its abundance of carbon dioxide. The comet also carries traces of water, carbon monoxide, cyanide, and even the rare shimmer of atomic nickel. These substances, though disparate in nature, form a tapestry of chemical complexity that defies the simplicity of its icy exterior. What do these chemicals reveal about the origins of 3I Atlas? How do they echo the processes that birthed the building blocks of life? As we peer into the coma of this interstellar wanderer, we are not merely observing a passing object. We are deciphering a message written in the universal language of atoms and bonds, a message that stretches across billions of years and light years. In the quiet glow of its coma, 3I Atlas invites us to contemplate the interconnectedness of the cosmos, where every molecule is a thread woven into the fabric of existence. The coma of 3I Atlas, that diffuse halo of gas and dust surrounding its nucleus, is a dynamic laboratory of chemical reactions. When sunlight strikes the comet's surface, it sublimates volatile ices, releasing a cascade of molecules into the vacuum of space. Among these are water vapor, accounting for roughly 1% of the total outgassing, and carbon monoxide, which escapes inches greater quantities. Yet the most intriguing component is cyanide, a molecule composed of carbon and nitrogen. Its linear structure resembling a molecular arrowhead, cyanide is not merely a poison, it is a fundamental building block of organic chemistry, a precursor to amino acids, the very scaffolding of proteins. Its presence in 3I Atlas suggests that the comet's parent body, long before it embarked on its interstellar voyage, harbored the raw ingredients for life. Even rarer is the detection of atomic nickel vapor, an element typically bound tightly within metallic alloys. Inch's planetary cores, the Very Large Telescope, VLT, revealed that this nickel exists in Inch's gaseous form, liberated by the intense energy of solar radiation. Such a phenomenon is unprecedented in Inches, the comets of our own solar system, where nickel remains sequestered in Inches rocky or metallic matrices. The release of atomic nickel implies that 3I Atlas's nucleus is not a mere conglomerate of ice and dust, but a relic of a different kind of planetary chemistry, one shaped by conditions alien to our own cosmic neighborhood. These molecules do not arise haphazardly. Their formation requires specific temperatures, pressures, and radiation environments. For instance, cyanide is synthesized in the cold, shadowy depths of molecular clouds, where ultraviolet light from nearby stars fractures simpler compounds, allowing carbon and nitrogen to bond. Carbon monoxide, on the other hand, forms in the frost-covered surfaces of interstellar grains, where hydrogen atoms collide with carbon atoms locked in ice. The presence of these molecules in 3I Atlas indicates that its birthplace was a region of the galaxy where such processes thrived, a cold, dark expanse where the seeds of chemistry were sown eons ago. Yet the most enigmatic aspect of the comet's chemistry is its carbon dioxide. Unlike the water and carbon monoxide, which are common in solar system comets, carbon dioxide dominates the outgassing of 3I Atlas. The James Webb Space Telescope, JWST, has measured this CO2 in staggering proportions, dwarfing the contributions of other volatiles. Why is this so? One hypothesis is that 3I Atlas formed in a region of its home star system, where temperatures were low enough for carbon dioxide to condense into ice, but too high for methane or ammonia to survive. Such a scenario would require a delicate balance of conditions, a thermal sweet spot in the protoplanetary disk of a distant sun. The combination of these molecules paints a picture of a comet born in a chemically distinct environment. Its chemistry is not a mirror of our own solar system's comets, but a reflection of a different cosmic history, one where the interplay of stellar winds, supernova shocks, and the slow drift of molecular clouds sculpted a unique inventory of materials. To study 3i Atlas is to glimpse a parallel universe of chemistry, where the same elements conspire into unfamiliar forms. What does the chemistry of 3i Atlas mean for our understanding of the cosmos? The presence of cyanide, Inch's particular, is a tantalizing clue. Inch's the search for the origins of life. On Earth, cyanide played a paradoxical role. Inch's the emergence of biology. Toxic Inch's high concentrations, yet essential Inch's the synthesis of nucleobases like adenine and guanine, the genetic alphabet of DNA. If 3i Atlas carries such molecules, it suggests that the precursors to life are not confined to our solar system, but are distributed throughout the galaxy. Could interstellar comets like this one have seeded young planets with the molecular ingredients for biochemistry? The answer may lie Inch's the isotopic ratios of carbon and nitrogen. Inch's 3i Atlas's cyanide, a signature that could reveal whether this molecule was forged. Inch's a stellar nebula, or Inch's the frigid outskirts of a planetary system. The nickel vapor, meanwhile, offers a window into the geology of 3i Atlas's parent body. In our solar system, nickel is typically found Inch's the cause of differentiated planets, where it has sunk toward the center due to gravity. Yet here, it exists as a free atom. Inch's the Coma, liberated by solar heating. This implies that 3i Atlas's nucleus is either undifferentiated, lacking the layered structure of terrestrial planets, or that its internal composition is dominated by a type of rock or alloy that can release nickel under extreme conditions. Either way, it challenges our assumptions about the diversity of planetary materials. Inch's the galaxy. If 3i Atlas is representative of its class, then interstellar comets may originate from systems where planetary formation proceeded under radically different rules, producing bodies rich Inch's metals and refractory compounds. Perhaps most profoundly, the age of 3i Atlas, estimated at 7 to 14 billion years, positions it as a relic of the Milky Way's earliest days. The thick disk from which it hails is a population of stars and debris that predates the thin disk where our solar system resides. These ancient objects are characterized by their high vertical motion relative to the galactic plane, a testament to their long turbulent histories. If 3i Atlas is indeed over twice the age of our solar system, then its chemistry reflects a time when the galaxy was still forming, when supernovae were more frequent, and when the interstellar medium was richer. Inch's heavy elements. Studying this comet is akin to reading a fossilized record of cosmic evolution, a snapshot of a galaxy. Inch's its youth, yet the implications extend beyond astronomy. The discovery of 3i Atlas forces us to confront the limits of our knowledge. For centuries, we believed comets to be the archetypal messengers of the early solar system, preserving the conditions of its birth. Now, with the arrival of interstellar visitors, we realize that comets are not just time capsules but galactic nomads, carrying the legacies of countless other stars and systems. Each one is a puzzle piece. Inch's a mosaic we have barely begun to assemble. What other surprises await us? Inch's the deep freeze of interstellar space. As we marvel at the chemical richness of 3i Atlas, another question lingers. Inch's the shadows of observation. How do we distinguish a comet from an asteroid when these objects approach from the depths of interstellar space? The line between these two categories is often blurred, defined not by inherent differences, but by behavior. Comets, with their volatile ices, outgas when warmed by the sun, producing comas and tails that betray their nature. Asteroids, by contrast, are inert rocks, their surfaces unchanged by solar radiation. Yet 3i Atlas itself straddles this boundary. Its coma reveals its identity as a comet, but its trajectory and composition hint at a history unlike any Inch's our solar system. In the next chapter, we will explore the tools and techniques that allow astronomers to unravel this mystery, peering into the hearts of interstellar travelers to determine whether they are icy wanderers or stony relics of distant worlds. The answers will not only refine our understanding of these objects, but deepen our appreciation for the vast interconnected web of matter that spans the cosmos. In the vast tapestry of the cosmos, where stars flicker like distant memories and galaxies spiral Inch's silent symphonies, an interloper arrives. It is not born of the sun, nor bound to the gravitational embrace of our solar system. Instead, It hails from the far reaches of interstellar space, a relic of an ancient epoch, hurtling through the void with a story etched in ice and gas. This is 3I Atlas, the third confirmed interstellar object to grace our cosmic neighborhood, and perhaps the oldest comet ever observed. Discovered on 1 July 2025 by the Atlas Survey Telescope in Chile. Its arrival sparks a profound question. What secrets does this traveler carry from the primordial depths of the Milky Way? 3I Atlas is no ordinary comet. Its trajectory defies the familiar elliptical paths of solar system objects. It follows a hyperbolic arc, a cosmic escape route from the sun's influence. Moving at a blistering 58 kilometers per second, it arrives with a velocity too great to have originated within our celestial backyard. Yet, its journey is not merely a passage. It is a message inches a bottle, cast adrift by the tides of stellar evolution. To study 3I Atlas is to peer into the past, to trace its origins to the Milky Way's thick disk, a region teeming with ancient stars. If the calculations hold, this comet may be over 7 billion years old, older than the solar system itself. Such a discovery challenges our understanding of the universe's history and the processes that shape its denizens. But how do we unravel the mysteries of this interstellar wanderer? How do we distinguish its icy heart from the veils of gas and dust that obscure it? And what does its presence tell us about the unseen currents of matter drifting through the galaxy? As we embark on this exploration, we are reminded that the universe is not a static expanse but a dynamic, interconnected web. 3I Atlas is not just a visitor, it is a thread inches the grand tapestry of cosmic history, waiting to be woven into our knowledge. The discovery of 3I Atlas was both serendipity and precision. On that fateful night in Chile, the Atlas telescope captured a faint smudge against the backdrop of the galactic center, a region notoriously crowded with stars. Initially catalogued as A11 Pillar 3Z, the object's trajectory raised immediate intrigue. Its velocity, 61 kilometers per second relative to the Sun, was anomalous. Unlike asteroids or comets native to the solar system, which follow closed orbits dictated by the Sun's gravity, 3I Atlas was on a one-way journey. Follow-up observations revealed a hyperbolic path, a curve so open that it would never return. This trajectory, combined with its high hyperbolic excess velocity, left no doubt. The object had originated beyond the confines of our planetary system. Yet the question of what 3I Atlas truly was lingered. Early images failed to resolve a coma, the telltale halo of gas and dust that distinguishes comets from asteroids. For days, astronomers debated whether this interstellar intruder was a rocky asteroid or an icy comet. The answer emerged from the skies themselves. Telescopes like the Hubble and James Webb Space Telescope pierced the veil of uncertainty, revealing spectral signatures of carbon dioxide, water vapor, and cyanide. These volatile compounds, activated by the sun's heat, confirmed the presence of a nucleus cloaked in ice. The comet's coma, though faint, was real, a fragile envelope of material liberated by the sun's touch. The comet's journey through the inner solar system unfolded like a slow-motion ballet. By October 2025, it would reach perihelion, the point of closest approach to the Sun, at 1.36 AU, straddling the orbits of Earth and Mars. Yet even at this proximity, 3I Atlas remained a ghostly specter, its peak brightness barely reaching magnitude 11.5, invisible to the unaided eye. Observers on Earth had to contend with its fleeting visibility, as it vanished behind the Sun's glare during perihelion, only to reappear inches the pre-dawn sky weeks later. For planetary scientists, this posed a unique challenge: to study an object that refused to linger, a transient guest inches a cosmic theater. What set 3I Atlas apart from its interstellar predecessors, 1I Oumuamua and 2I Borisov, was its origin. While the first two hailed from the Milky Way's thin disk, a younger, dynamically active region, 3I Atlas traced back to the thick disk, a denser, older population of stars. This distinction hinted at a different cosmic provenance, one shaped by the galaxy's ancient history. The thick disk, a relic of the Milky Way's formative years, is home to stars with lower metallicity, forged inches an era when heavy elements were scarce. If 3I Atlas indeed originated here, it carried within it the chemical fingerprints of a time before the solar system's birth. To determine 3I Atlas's age, astronomers turned to the language of motion by decomposing its hyperbolic excess velocity into galactic coordinates. Researchers reconstructed its path through the Milky Way. The results were staggering. The comet approached the solar system with a vertical velocity of 18.5 kilometers per second, propelling it upward through the galactic plane. This trajectory, combined with its radial velocity of 51.0 kilometers per second, moving away from the galactic center, placed it firmly within the thick disk population. Stars inches this region are typically billions of years old. Their orbits tilted relative to the galaxy's midplane. For 3I Atlas to belong here meant it was not a mere interstellar drifter, but a survivor of epochs long gone. Estimates of its age, derived from statistical models of stellar populations, painted a picture of antiquity. With a 68% probability, 3I Atlas was between 7.6 and 14 billion years old, far exceeding the solar system's 4.6 billion year history. Some analyses suggested an even broader range, from 3 to 11 billion years, but all converged on a singular truth. This comet predates the Sun by eons. Its nucleus, encased inches ancient ices, may contain molecules formed inches the protoplanetary disks of stars that no longer exist. If so, 3I Atlas is not just a visitor, it is a fossil of the Milky Way's youth, a relic of an era when the galaxy was still assembling its spiral arms and forging its chemical diversity. The implications of this discovery ripple outward. If interstellar objects like 3I Atlas are common, they could serve as cosmic messengers, carrying samples of alien chemistry into the solar system. Their study might reveal the building blocks of life beyond our corner of the galaxy. Moreover, the fact that 3I Atlas originated from the southern celestial hemisphere challenges previous assumptions about interstellar object distribution. Earlier models predicted a bias toward the solar apex, the direction of the sun's motion through the galaxy. Yet 3I Atlas's southern origin suggests either a statistical anomaly or a need to revise our understanding of how interstellar bodies migrate through the galaxy. Even the comet's composition offers clues to its origins. Unlike the water-rich 2I Borisov, 3I Atlas is unusually rich in carbon dioxide, a molecule more commonly associated with cold, distant regions of the galaxy. Its emissions of cyanide, an atomic nickel vapor, further hint at a formation environment distinct from those of solar system comets. These differences underscore the diversity of interstellar objects and the myriad ways planetary systems evolve across the cosmos. Each comet, each asteroid, is a fragment of a story written inches the stars, a narrative we are only beginning to decipher. Yet, for all the insights 3I Atlas provides, its nucleus remains a mystery shrouded inches gas and dust. Unlike the solid, rocky surfaces of asteroids, comets are dynamic entities. Their surface is constantly eroding as ices sublimate and jets of material erupt into space. For 3I Atlas, this volatility complicates efforts to measure its size. Observations suggest a nucleus no larger than 1 kilometer across, but the Coma's glare obscures precise measurements. To pierce this veil, astronomers rely on indirect methods: spectroscopy to analyze gas composition, thermal imaging to detect heat signatures, and radar to probe the nucleus's structure. The challenge extends beyond technique. 3I Atlas's fleeting visibility demands rapid, coordinated observations from telescopes around the world. Its passage through the inner solar system is a race against time, a window of opportunity to gather data before it vanishes into the depths of space. Yet, this urgency is a testament to the resilience of science. From the crowded starfields of the galactic center to the remote deserts of Chile, the discovery of 3I Atlas is a reminder that the universe reveals itself to those who dare to look. As we turn our gaze to the next chapter of this cosmic tale, we are left with questions that transcend the comet itself. How many more interstellar visitors lurk inches the darkness, undetected by our current instruments? What other histories lie encoded inches their trajectories and compositions? And what might these travelers teach us about the origins of life? the evolution of galaxies, and the interconnectedness of the cosmos. The journey of 3i Atlas is not an end but a beginning, a spark igniting the quest to understand our place, inches the infinite. This script adheres to the requested structure, weaving scientific detail with a contemplative narrative. Each section builds upon the last, emphasizing the cosmic significance of 3i Atlas, while maintaining clarity and wonder. The transition to future exploration invites readers to ponder the broader implications of interstellar objects, ensuring the script serves as both an informative and inspiring account of this celestial visitor. In the vast, dark expanse of the cosmos, where time stretches into epochs and distances blur the boundaries of comprehension, 3i Atlas glides, a silent, icy traveler from the distant reaches of the Milky Way. Discovered inches, July 2025. This interstellar comet has captured the imagination of scientists and dreamers alike, not merely for its rarity but for the profound mystery it carries. As it hurtles toward perihelion on 29 October 2025, its nucleus remains hidden, cloaked by a swirling veil of gas and dust known as the Coma. Like a ghostly figure inches a fog-laden forest, the nucleus of 3i Atlas defies direct observation, its true size and shape obscured by the very activity that makes it a comet. Yet within this enigma lies a story of cosmic origins, a tale of how a single object born inches a stellar nursery billions of years ago has traversed the void to cross paths with our solar system. What is it about the nucleus of 3i Atlas that makes it so elusive? The answer lies inches the nature of comets themselves, fragile, volatile constructs of ice, rock, and organic compounds held together by gravity's tenuous grip. When sunlight strikes a comet's nucleus, the heat triggers a process called sublimation, where frozen gases transform directly into vapor, carrying with them particles of dust and debris. This creates the Coma, a luminous halo that expands outward, scattering light and blurring the edges of the nucleus. For 3i Atlas, this phenomenon has turned its core into a riddle, a puzzle that demands not only technological ingenuity, but also a reimagining of how we perceive the building blocks of the universe. To peer beyond the Coma is to glimpse the raw materials of planetary formation, preserved inches of frozen time capsule from an alien star system. Yet, even as telescopes like Hubble and James Webb strain their lenses to unravel this secret, the nucleus remains a phantom, its dimensions a statistical range rather than a certainty. This uncertainty is not a failure of science, but a testament to the humility required inches the face of the cosmos. 3i Atlas reminds us that the universe is not always willing to yield its truths easily, and perhaps it is inches the act of seeking, rather than finding, that we begin to understand the grandeur of our own insignificance. The Coma of 3i Atlas is not merely a passive shroud, it is a dynamic, ever-changing phenomenon, shaped by the interplay of solar radiation, the comet's internal structure, and the chaotic dance of its volatile constituents. At its heart lies the nucleus, a solid body composed of water ice, carbon dioxide, methane, and silicate grains, all bound together inches a porous fractal architecture. Yet the Coma's brilliance, its shimmering, diffuse glow, obscures this nucleus, blending the light of the escaping gases and dust with the fainter reflection of sunlight off the nucleus itself. To isolate the nucleus, astronomers must disentangle these overlapping signals, a task akin to distinguishing the individual notes of a symphony buried beneath a cacophony of sound. One of the primary tools inches this endeavor is high-resolution imaging, particularly from space-based observatories. Hubble's Advanced Camera for Surveys, ACS, has captured images of 3i Atlas at wavelengths sensitive to the scattering properties of the Coma's particles. By analyzing the spatial distribution of light, researchers can model how much of the observed brightness originates from the Coma versus the nucleus. Current estimates suggest the nucleus spans between 0.32 and 5.6 kilometers diameter, though the most probable size is less than 1 kilometer. This wide range reflects the difficulty of separating the nucleus's faint signature from the Coma's overwhelming presence. Beyond imaging, Techniques such as polarimetry and thermal modeling offer complementary insights. Polarimetry measures the polarization of light scattered by the coma, revealing clues about the size and composition of dust particles. For example, larger grains tend to polarize light differently than smaller ones, allowing scientists to infer the dominant particle sizes inches the coma. Thermal modeling, on the other hand, tracks the infrared emission from the nucleus and coma, distinguishing the heat signatures of the two components. These methods collectively paint a picture of a nucleus that is likely irregular inches shape, with a surface marred by craters and fissures, and a coma dominated by fine submicron dust grains, mixed with complex organic molecules. The James Webb Space Telescope, JWST, has added another layer to this investigation. Its unprecedented sensitivity to mid-infrared wavelengths has detected the spectral fingerprints of carbon dioxide and water ice inches the coma, alongside trace amounts of carbon monoxide and carbonyl sulfide. These volatile compounds suggest that the nucleus is not a homogeneous body, but a mosaic of distinct reservoirs, each contributing to the comet's activity. The detection of cyanide gas and atomic nickel vapor by the Very Large Telescope, VLT, further complicates the picture, hinting at chemical processes that may mirror those occurring inches the early solar system. Together, these observations underscore the complexity of 3I Atlas, not as a simple icy lump, but as a chemically rich, geologically diverse world. Yet, for all the data amassed, the nucleus remains a statistical construct. No single observation has resolved its exact size or morphology. This ambiguity is not a limitation, but a feature of the scientific method. Inches the absence of definitive evidence. Hypotheses are tested against the constraints of available data, refining our understanding with each iteration. The case of 3I Atlas exemplifies this iterative process, where every new observation narrows the possibilities, guiding us closer to the truth without ever fully capturing it. The inability to directly resolve the nucleus of 3I Atlas raises profound questions about the nature of interstellar comets and their role inches the cosmic story. If the nucleus is smaller than 1 kilometer, as current models suggest, its low mass implies a high degree of porosity or a fragile, loosely bound structure. Such a configuration would make it susceptible to disruption under the stresses of solar heating, potentially leading to catastrophic fragmentation as it nears perihelion. Conversely, if the nucleus is larger, its greater mass could indicate a denser, more coherent body, capable of surviving the harsh conditions of the inner solar system. Either scenario challenges our assumptions about the resilience of interstellar objects and their capacity to endure the rigors of interstellar travel. This uncertainty also complicates efforts to determine the comet's internal structure. AMPA's porous nucleus might suggest a formation history involving gentle accretion, where icy grains aggregated over millions of years inches a low-density environment. AMPA's denser nucleus, by contrast, could imply violent collisions or gravitational compression, processes more commonly associated with the turbulent disks of young star systems. Given that 3I Atlas hails from the Milky Way's thick disk, a region populated by ancient stars with metal-poor compositions, its formation environment likely differed starkly from that of the solar system. Understanding the nucleus's structure is thus key to reconstructing the conditions under which it formed, offering a window into the diversity of planetary building blocks across the galaxy. Moreover, the unresolved nature of the nucleus highlights the limitations of remote sensing inches probing the fundamental properties of interstellar objects. While telescopic observations provide invaluable data, they remain indirect measurements, filtered through the noise of the coma and the biases of observational technique. To truly unlock the secrets of 3I Atlas, a direct mission, such as a flyby or sample return, would be necessary. Such a venture would not only resolve the nucleus's size and shape, but also analyze its chemical composition inches situ, revealing the isotopic ratios and mineralogical signatures that betray its extraterrestrial origins. Until then, the comet remains a tantalizing enigma, its nucleus a symbol of the unknown. The philosophical implications of this uncertainty are equally compelling. In a universe governed by entropy and chaos, 3I Atlas embodies the tension between order and disorder, preservation and decay. Its nucleus, if indeed fragile, may disintegrate entirely by the time it reaches perihelion, scattering its ancient materials into the void, or it may endure, a relic of a bygone era that continues its journey beyond the solar system, carrying with it the memory of a star long extinguished. Either outcome speaks to the impermanence of cosmic structures and the fleeting nature of observation. For humans, who can only witness this passage from a single vantage point, the comet becomes a reminder of the limits of knowledge and the enduring allure of the unknown. As 3i Atlas arcs through the solar system on its hyperbolic trajectory, it joins the ranks of two other interstellar interlopers, 1i Oumuamua and 2i Borisov. These three objects, each a product of alien star systems, serve as cosmic messengers, bearing fragments of their homeworlds across the gulf of interstellar space. Yet, 3i Atlas stands apart in both its chemistry and origin. Unlike Oumuamua, whose elongated shape and lack of coma defied easy classification, or Borisov, which exhibited a familiar cometary structure akin to those of the solar system, 3i Atlas reveals a composition rich in carbon dioxide and volatile gases, suggesting a formation environment colder and more chemically diverse than those of its predecessors. The comet's origin inches the thick disk of the Milky Way, a region dominated by old metal-poor stars, further distinguishes it, while Oumuamua and Borisov likely hailed from the thin disk, a younger, more metal-rich population of stars. 3i Atlas's trajectory traces back to a realm where stellar evolution has progressed for billions of years. This places it among the oldest known interstellar objects, its nucleus potentially predating the solar system itself. Such an object is not merely a visitor, but a relic of a time when the Milky Way was still assembling its present form, a time when the first generations of stars ignited and forged the heavy elements that now permeate the cosmos. In this light, 3i Atlas becomes more than a scientific curiosity. It is a bridge between epochs, a fragment of the universe's deep past carried forward by the relentless currents of gravity and chance. Its passage through the solar system is a fleeting encounter, a momentary alignment of two isolated systems, separated by eons of time and space. Yet inches that moment lies the potential for transformation, to refine our understanding of planetary formation, to challenge our assumptions about the diversity of interstellar objects, and to inspire a deeper appreciation for the interconnectedness of the cosmos. As 3i Atlas fades from view, its legacy will endure inches the data it leaves behind and the questions it ignites. What other interstellar travelers await discovery? Their trajectories hidden by the glare of the galactic center. What stories do their nuclei hold, waiting to be deciphered by future generations of explorers? In the silent dance of Coma and Nucleus, we find not only the mysteries of a single comet, but the infinite possibilities of a universe that refuses to be fully known. In the vast silent expanse of the cosmos, where time stretches into eons and distances dwarf human comprehension, a lone traveler drifts through the void. This is 3i Atlas, an interstellar comet born inches the crucible of another star system, now passing through our own, with a speed and trajectory that defy the gentle rhythms of the solar system. Its arrival is a fleeting moment. A cosmic blink inches the grand tapestry of the universe, but it carries within it the echoes of ancient worlds and the promise of answers to questions we have barely begun to ask. For millennia, humanity has gazed upward, seeking meaning inches the stars. Yet even inches this age of advanced astronomy, the universe still surprises us. The discovery of 3i Atlas inches July 2025 by the Atlas Telescope inches Chile marks a milestone inches our understanding of the cosmos. It is not merely a visitor from beyond our stellar neighborhood. It is a relic of an alien epoch, a time when the Milky Way was young and chaotic. As it hurtles through the inner solar system, its icy heart warmed by the sun, it becomes a bridge between the familiar and the unknown, a testament to the boundless scale of existence. What makes 3i Atlas unique is not just its origin, but its nature. Unlike the first interstellar interloper, 1i Oumuamua, a cigar-shaped enigma that defied classification, It bears the unmistakable signs of a comet, a glowing coma and a tail of gas and dust. Yet it differs from the second interstellar comet, 2I Borisov, inches ways that hint at entirely new astrophysical processes. 3I Atlas is a puzzle wrapped inches mystery, its carbon dioxide-rich composition and traces of atomic nickel, suggesting a history unlike anything seen inches our own backyard. To study it is to peer into the life cycles of distant stars, to trace the birth and death of worlds across the galaxy. This is the story of 3I Atlas, not just as an object of scientific inquiry, but as a symbol of the universe's capacity to inspire awe. In its brief passage, it reminds us that we are part of something far greater. A single thread inches a web of infinite complexity. As we follow its journey, we are invited to contemplate our place inches the cosmos and the enduring quest to understand the forces that shape all things. When 3I Atlas was first detected inches July 2025, it was already a traveler through the inner solar system, its path illuminated by the glare of the sun at 4.5 astronomical units, AU, over 670 million kilometers from the sun. It moved at a blistering 58 kilometers per second, faster than any natural object inches our system, except those ejected by gravitational slingshots. This speed, combined with its hyperbolic trajectory, revealed an inescapable truth. 3I Atlas was not bound to the sun. It was a transient, a visitor from the depths of interstellar space. The comet's origin lies inches the Milky Way's thick disk, a region populated by ancient stars whose lifetimes stretch back billions of years. This places 3I Atlas among the oldest known objects, inches the universe, potentially predating the solar system itself. Its journey to us is a testament to the dynamic nature of the galaxy, where gravitational interactions between stars and the immense tidal forces of the galactic core can eject comets into the void. Over eons, these wanderers drift, their orbits shaped by the unseen hands of cosmic tides, until they cross paths with a new star system. What makes 3I Atlas particularly intriguing is its composition. While most comets inches our solar system are rich inches water ice, 3I Atlas is dominated by carbon dioxide, a substance that sublimates at much lower temperatures. This suggests it formed inches an environment colder than the Kuiper Belt, the icy reservoir of our own system. Observations by the James Webb Space Telescope revealed traces of water vapor, carbon monoxide, and carbonyl sulfide. But it is the presence of cyanide gas and atomic nickel vapor that truly sets it apart. These elements, typically associated with extreme conditions, hint at a violent or unusual formation history. Could 3I Atlas have originated inches a star-forming nebula, where shockwaves forged heavy elements? Or perhaps it was once part of a shattered planet, its remnants scattered into the void. The comet's nucleus remains shrouded inches uncertainty, with a diameter estimated between 0.32 and 5.6 kilometers. It is small enough to be fragile, yet its activity is surprisingly robust. The sun's heat drives sublimation of its ices, releasing gas and dust that form a coma and a faint tail. This process, familiar to us from the behavior of solar system comets like Halley's, is amplified here by the comet's unique chemistry. The Hubble Space Telescope's images suggest a nucleus no larger than 1 kilometer, yet its coma glows with the intensity of a much larger body. This discrepancy underscores the challenges of observing interstellar objects. Our tools must pierce the veil of distance and perspective to glimpse their true nature. As 3I Atlas approaches perihelion on October 29, 2025, it will come within 1.36 AU of the Sun, a point between the orbits of Earth and Mars. Though it will not pose a threat to our planet, its closest approach offers a fleeting window for observation. Telescopes on Earth and inches space will track its evolution, measuring changes inches brightness, composition, and structure. Will its nucleus disintegrate under the sun's relentless heat, or will it endure? A resilient survivor of interstellar travel, the answers lie inches the data we collect, a mosaic of light and shadow pieced together across continents and instruments. The discovery of 3I Atlas is more than a triumph of technology. It is a gateway to understanding the architecture of planetary systems beyond our own. For centuries, astronomers have assumed that comets and asteroids are the detritus of planet formation, the leftover building blocks that failed to coalesce into worlds. Yet 3I Atlas challenges this assumption. Its chemical fingerprint, dominated by carbon dioxide and laced with exotic compounds, suggests a formation environment unlike anything inches the solar system. If we can decode its origins, we may uncover new pathways for planetary formation, perhaps even clues to the existence of alien oceans or atmospheres. One of the most profound implications of 3I Atlas is its age. Estimated to be between 7.6 and 14 billion years, it predates the solar system by threefold. Such an object is a relic of the Milky Way's early days, a time when stars were younger and more volatile. Its survival through eons of galactic turbulence raises questions about the resilience of cometary bodies. How many such wanderers exist inches the interstellar medium, invisible until their paths intersect with a star system? And what can their chemical diversity tell us about the evolution of galaxies themselves? The comet's trajectory also reveals a cosmic bias. While Oumuamua and Borisov originated from the northern celestial hemisphere, 3I Atlas hails from the south, a region less explored due to the dense star fields near the galactic center. This asymmetry may reflect the uneven distribution of interstellar objects, or it may indicate flaws inches our observational strategies. Either way, 3I Atlas serves as a reminder that our view of the universe is still incomplete. Future surveys must cast wider nets, scanning both hemispheres to capture the full breadth of interstellar traffic. Perhaps most tantalizing is the possibility that 3I Atlas is not an anomaly, but a harbinger of a new class of interstellar object. Its CO2-rich composition and atomic nickel suggest processes unique to its home system, perhaps one where stellar winds or supernova shocks sculpted the raw materials of planets. If such objects are common, they could revolutionize our understanding of the cosmos. They might carry organic molecules essential to life, or they might preserve the signatures of long-dead stars. In either case, they are messengers from the furthest reaches of space, bearing gifts of knowledge for those willing to listen. Yet for all its revelations, 3I Atlas is also a reminder of our limitations. Its faintness, its fleeting visibility, and the difficulty of separating its nucleus from its Coma highlight the challenges of studying interstellar visitors. We are like children peering through a fog, trying to discern patterns inches the chaos. But each new discovery sharpens our vision, drawing us closer to the truth. And as 3I Atlas fades into the night, it leaves behind a question that will echo through the decades. What else lies beyond our horizon, waiting to be found? As 3I Atlas recedes from the sun, its path carved into the fabric of the cosmos, we are left to ponder the deeper mysteries it unveils. Chief among them is the question of why southern origin interstellar objects are so rare. For decades, astronomers theorized that the majority of interstellar travelers would originate from the solar apex, the direction inches which the sun is moving through the galaxy. The discovery of 3I Atlas coming from the opposite hemisphere disrupts this expectation. Is it a statistical fluke, or does it signal an unseen abundance of southern-born comets? The answer may lie inches the biases of our instruments, which struggle to penetrate the dense star fields near the galactic center. This realization compels us to refine our methods, to look beyond the familiar and into the obscured. Future missions, equipped with adaptive optics and next-generation spectroscopy, will probe the southern skies with renewed vigor. Perhaps we will find that interstellar objects are not randomly distributed, but clustered inches regions, where stellar nurseries and galactic tides conspire to launch them into the void. Or maybe 3I Atlas is a singular outlier, a cosmic anomaly that will take generations to decipher. Either way, its journey reminds us that the universe is a vast, untamed frontier, one that demands humility, patience, and an unyielding curiosity. And so, as we turn our gaze to the stars, we do so with the knowledge that we are not alone inches the dark. The cosmos teems with stories waiting to be told. Each interstellar visitor a chapter inches the epic of creation. 3I Atlas is but one of many. A fleeting whisper inches the eternal symphony of the universe. Its tale is not an end, but a beginning, a call to explore, to wonder, and to seek the truths hidden inches the light of distant stars. The universe is a vast ocean of mystery, its currents carrying fragments of distant worlds across the void. Among these travelers, interstellar objects like 3i Atlas stand as celestial messengers, whispering tales of their origins inches the cold, ancient reaches of the cosmos. Yet, the story of 3i Atlas is not merely one of a comet's journey. It is a profound challenge to our understanding of where such wanderers come from and how often they visit our solar system. Discovered inches the crowded, star-drenched skies near the Milky Way's heart. 3i Atlas emerged from a region long thought to be a dead zone for interstellar observers. Its arrival defied expectations, revealing a hidden bias inches our cosmic census and igniting a new chapter inches the search for extraterrestrial visitors. For centuries, humanity has gazed upward, mapping the heavens with telescopes and imagination. But even with our most advanced instruments, the southern celestial hemisphere remains a frontier of uncertainty. The galactic center, a region teeming with stars and veiled by interstellar dust, creates a cosmic fog that obscures faint objects. Here, the density of stars rivals the brilliance of 1,000 suns, drowning out the subtle glimmers of passing comets. It is inches this shadowed expanse that 3i Atlas was born. Yet its detection was not inevitable. The very act of spotting it required overcoming a barrier of light and darkness, a testament to the ingenuity of modern astronomy and the persistence of those who peer into the unknown. This comet's origin is a riddle wrapped inches a paradox. While models once predicted that interstellar visitors would predominantly hail from the northern sky, the direction of the sun's motion through the galaxy, 3i Atlas arrived from the south. Its trajectory, steeped inches the gravitational tides of the Milky Way, suggests a connection to the galaxy's ancient thick disk, a realm of stars older than the solar system itself. The discovery of 3i Atlas is more than a footnote inches the annals of astronomy. It is a call to re-examine our assumptions, to question whether the universe's interstellar highway is as well traveled as we believed, or if we've simply been looking inches the wrong direction. To understand why 3i Atlas's discovery is so remarkable, we must first confront the limitations of our observational tools. Telescopes, despite their sophistication, are bound by the physics of light and the geometry of the sky. The southern celestial hemisphere, particularly near the galactic center, is a labyrinth of stellar congestion. Here, the Milky Way's spiral arms converge, their billions of stars creating a luminous backdrop that drowns out faint interlopers. Dust clouds further complicate matters, scattering and absorbing starlight, leaving astronomers with a fragmented view of the cosmos. In this environment, a comet like 3i Atlas, small, dim, and moving against the grain of galactic motion, is nearly invisible. The problem is not merely one of brightness, it is a matter of perspective. Most large-scale sky surveys, such as the Zwicky Transient Facility (ZTF) and the Asteroid Terrestrial Impact Last Alert System (ATLAS), are optimized for the northern sky. These surveys prioritize regions where the galactic plane arcs overhead, allowing for clearer, deeper observations. The southern sky, by contrast, is often a secondary focus, its data scrutinized less rigorously. This bias inches observational strategy has created a blind spot inches our cosmic census, a gap that 3i Atlas's discovery now highlights. When 3i Atlas was first glimpsed by the Atlas telescope, inches Chile on 1 July 2025, it was already a ghost inches the machine. Its path through the galactic center meant it passed through a region where automated detection algorithms struggled to distinguish it from the sea of stars. Pre-discovery observations from the ZTF and amateur astronomer Sam Dean revealed that the comet had lingered inches this chaotic backdrop for weeks, its presence masked by the sheer density of celestial bodies. Only when its trajectory began to diverge from the galactic plane did its true nature emerge, a hyperbolic curve that betrayed its interstellar origin. Theoretical models had long predicted that interstellar objects would arrive from the solar apex, the direction of the sun's motion relative to the local standard of rest. These models assumed that gravitational interactions inches the outer reaches of neighboring star systems would slingshot debris into interstellar trajectories, favoring the direction of the sun's galactic journey. Yet 3I Atlas arrived from the opposite hemisphere, a fact that forced astronomers to reconsider their assumptions. Was this comet an anomaly, a statistical outlier, inches a rare cosmic lottery, or was it a harbinger of a larger, unseen population of interstellar travelers originating from the south? The answer lies inches the numbers. Statistical analyses of interstellar object detections suggest that our current tally is skewed. Surveys covering the northern sky have identified 2 confirmed interstellar visitors, 1I Oumuamua and 2I Borisov, while the southern hemisphere has yielded only 3I Atlas. However, this discrepancy may not reflect actual scarcity, but rather the limitations of our observational tools. If the southern sky is indeed a prolific source of interstellar comets, then our current methods are failing us. The detection of 3I Atlas serves as a wake-up call. The universe may be teeming with interstellar wanderers, but we are only beginning to see them. The implications of 3I Atlas's discovery ripple outward, challenging the foundations of our cosmic cartography. For decades, astronomers have built models of interstellar object distribution based on limited data, assuming that the solar apex is the primary corridor for these visitors. Now, with evidence of a southern origin comet, the model must be revised. Are interstellar comets evenly distributed throughout the galaxy? Or do they cluster inches-specific regions? Does the Milky Way's gravitational architecture favor certain pathways, channeling debris from ancient star systems toward the solar system? One possibility is that the southern hemisphere is simply more abundant inches interstellar debris. If this is true, it would mean that our current surveys have missed a significant portion of the interstellar population. Another theory posits that the southern sky's observational challenges have suppressed our ability to detect these objects, creating the illusion of scarcity. Either way, the discovery of 3I Atlas underscores the need for a more comprehensive approach to interstellar object detection. To address this gap, future surveys must adapt to the unique challenges of the southern sky. Instruments like the Vera Rubin Observatory's Legacy Survey of Space and Time, LSST, promise to revolutionize our capabilities, scanning the entire sky with unprecedented sensitivity. By prioritizing the southern hemisphere and employing advanced algorithms to filter out foreground stars, these surveys could uncover a flood of new interstellar visitors. Additionally, collaborations with amateur astronomers, who often monitor the skies with undivided attention, may prove invaluable. Their contributions, as demonstrated by Sam Dean's pre-discovery observations of 3I Atlas, highlight the power of citizen science inches overcoming observational biases. Beyond detection, the study of 3I Atlas offers insights into the formation and evolution of planetary systems. Its composition, rich inches carbon dioxide and containing traces of water ice, carbon monoxide, and cyanide, hints at a history shaped by the conditions of its parent star system. Unlike the icy bodies of the solar system, which formed inches the cold outer reaches, 3I Atlas may originate from a star system with a different chemical fingerprint. By analyzing its volatile content, scientists can piece together the environmental conditions of its birthplace, offering a window into the diversity of planetary systems across the galaxy. Moreover, 3I Atlas's age, estimated at 7.6 to 14 billion years, places it among the oldest known objects, inches the universe. This antiquity raises intriguing questions about the longevity of interstellar comets. Could such bodies survive the violent gravitational tides of the Milky Way for billions of years? Or was 3I Atlas ejected from its home system, inches a cataclysmic event, only to drift through the galaxy until its fateful encounter with the solar system? These questions demand answers that lie beyond the scope of a single discovery, requiring a broader census of interstellar objects to establish patterns and anomalies. The exploration of 3I Atlas also invites philosophical reflection. As we trace its path back through the cosmos, we are reminded of our own place, inches the grand scheme of things. The comet is not merely a visitor, it is a relic of a time before the solar system, a fragment of a forgotten star system that now shares our corner of the galaxy. In studying it, we engage inches a dialogue with the past, decoding the whispers of a civilization or natural process that predates our own. Such encounters humble us, grounding our scientific inquiries inches the awe-inspiring reality of an infinite universe. As 3i Atlas continues its journey through the solar system, its trajectory reveals more than just its origin. It tells a story of the Milky Way's structure, the comet's hyperbolic path, steeply inclined relative to the galactic plane, places it among the thick disk population of the galaxy. This ancient layer of stars, older and chemically distinct from the younger thin disk, is a remnant of the Milky Way's early days. The thick disk's gravitational dynamics may have played a role in shaping 3i Atlas's interstellar voyage, nudging it toward the solar system like a leaf caught inches a cosmic breeze. This connection between the comet's vertical motion and the Milky Way's architecture opens a new avenue of inquiry. How do the gravitational forces of the galaxy influence the paths of interstellar objects? What role does the thick disk play inches launching or capturing these wanderers? The answers lie inches the data, waiting to be uncovered as we refine our understanding of the galactic tides that govern the fate of objects like 3i Atlas. In the next segment, we will delve into the vertical velocity of this comet, tracing its descent through the Milky Way's layers and contemplating the secrets it holds about our galaxy's history. In the vast, uncharted expanse of the cosmos, where time stretches beyond comprehension and gravity weaves invisible threads through the fabric of space, a silent traveler emerged from the depths of interstellar darkness. On 1 July 2025, the Asteroid Terrestrial Impact Last Alert System, ATLAS, stationed at Rio Hurtado, Chile, captured the first glimpse of a celestial wanderer, 3i Atlas. This interstellar comet, hurtling through the solar system at an astonishing 58 kilometers per second, marked itself as the third confirmed visitor from beyond our stellar neighborhood. Unlike the fleeting whispers of its predecessors, 1i Oumuamua and 2i Borisov, 3i Atlas carried a unique signature, a vertical velocity that hinted at ancient origins and a journey spanning billions of years. Its arrival was not a mere accident of chance, but a profound reminder of the interconnectedness of galaxies, a testament to the dynamic dance of matter across the Milky Way. As scientists turned their instruments toward this enigmatic object, they were not merely observing a comet. They were peering into a relic of the universe's distant past, a cosmic artifact bearing secrets of the galactic thick disk and the turbulent history of our home galaxy. The story of 3i Atlas is one of discovery, wonder, and the humbling realization that we are but one voice inches the symphony of the cosmos. To understand 3i Atlas, we must first grasp the physics that govern its extraordinary journey. Unlike the periodic comets that originate from the Kuiper belt or Oort cloud, 3i Atlas follows a hyperbolic trajectory, a path that curves sharply around the Sun before escaping the solar system entirely. This trajectory is defined by its hyperbolic excess velocity, the speed at which the comet travels once the gravitational influence of the Sun becomes negligible. With a velocity of 58 kilometers per second relative to the Sun, 3i Atlas is moving faster than the escape velocity required to break free from our solar system, ensuring it will never return. Such speeds are impossible for objects born within the solar system unless they have been accelerated by a planetary encounter. Yet 3i Atlas's path reveals no such gravitational slingshot. Instead, its motion traces back to the Milky Way's thick disk, a region populated by ancient stars that drift through the galaxy on inclined, looping orbits. The hyperbolic nature of 3i Atlas's trajectory was confirmed through meticulous orbital calculations. Initial observations by Atlas detected the comet at a distance of 4.5 astronomical units, AU, from the Sun, already moving at a velocity far exceeding the solar system's average escape velocity. Follow-up data from the Zwicky Transient Facility, ZTF, and amateur astronomers like Sam Dean revealed pre-discovery images dating back to June 2025, allowing astronomers to reconstruct its path with precision. These observations painted a clear picture. 3i Atlas was not bound to the Sun's gravitational embrace. Instead, it was a transient visitor, a cosmic nomad whose origins lay inches the distant reaches of interstellar space. What makes 3I Atlas particularly intriguing is its composition. Like all comets, it consists of a nucleus, a solid core of ice, rock and organic compounds, surrounded by a coma, a gaseous envelope formed when solar radiation sublimates the nucleus's volatile materials. However, spectroscopic analysis by the James Webb Space Telescope, JWST, and the Very Large Telescope, VLT, unveiled a chemical profile unlike any seen in INCH's native solar system comets. The comet is unusually rich in carbon dioxide, with trace amounts of water ice, carbon monoxide, and carbonyl sulfide. Additionally, the detection of cyanide gas and atomic nickel vapor suggests a unique evolutionary history, perhaps shaped by the extreme conditions of its birthplace. These findings challenge our understanding of comet formation, hinting that interstellar comets may harbor chemistries distinct from their solar system counterparts. Yet perhaps the most profound revelation lies in INCH's 3I Atlas's age. Studies of its orbital mechanics and the properties of the thick disk population suggest it could be between 7.6 and 14 billion years old, far older than our 4.6 billion-year-old solar system. This staggering antiquity implies that 3I Atlas formed INCH as a different galactic environment, possibly INCH as a long-vanished stellar nursery or a disrupted protoplanetary disk. To imagine this comet as a relic of the early Milky Way is to confront the vastness of time itself. It has witnessed epochs we cannot fathom, drifting through the cosmos long before the sun ignited and the planets coalesced. In its frozen heart lies a record of the universe's infancy, waiting to be deciphered by human ingenuity. The discovery of 3I Atlas has upended long-standing assumptions about the origins and distribution of interstellar objects. Prior to its arrival, astronomers anticipated that most interstellar visitors would hail from the thin disk, the flattened plane, where younger stars, including our own, reside. These objects would travel on nearly flat trajectories, aligned with the galactic plane. However, 3I Atlas's origin inches the thick disk, a puffy spherical region populated by older stars, reveals a more complex story. The thick disk is a relic of the Milky Way's violent youth, a remnant of mergers with smaller galaxies and the gravitational upheavals that shaped our galaxy's structure. By tracing 3I Atlas's path, scientists have uncovered evidence that interstellar comets may originate from diverse galactic environments, each carrying a unique imprint of their birthplaces. This revelation raises profound questions about the Milky Way's evolutionary history. If thick disk comets like 3I Atlas are common, it suggests that the galaxy's early mergers and dynamical processes played a significant role, INCH's scattering debris across interstellar space. Moreover, 3I Atlas's southern origin, opposite to the solar apex, the direction of the sun's motion through the galaxy challenges predictions that interstellar objects would preferentially arrive from the north. This asymmetry hints at an uneven distribution of interstellar material, potentially influenced by the Milky Way's asymmetric spiral arms or the gravitational tides of neighboring galaxies. Such findings compel astronomers to refine their models of galactic dynamics, recognizing that the Milky Way is not a static entity but a living, evolving system. The vertical velocity component of 3I Atlas further complicates this narrative. With a Watts component of 18.5 kilometers per second, the comet is ascending through the galactic plane, a motion characteristic of thick disk stars. This upward trajectory implies that 3I Atlas's path is tilted relative to the galactic disk, a feature rarely observed in INCH's interstellar object. While Oumuamua and Borisov followed relatively flat paths, 3I Atlas's inclined orbit suggests a different mechanism of ejection from its parent star system. Perhaps it was flung from a binary star system, where gravitational interactions between two stars could generate the necessary energy to launch a comet into interstellar space. Alternatively, it may have originated INCH as a dense star-forming region, where supernovae or stellar winds expelled material into the void. Either scenario underscores the diversity of mechanisms that can produce interstellar objects, each reflecting the unique circumstances of its host environment. Furthermore, 3I Atlas's chemical composition offers tantalizing clues about the conditions inches its birthplace, the prevalence of carbon dioxide, and the absence of certain molecules found inches. Solar system comets indicate that its parent star system experienced different temperatures and pressures during its formation. These differences could stem from the star system's location inches the galaxy or the timing of its formation relative to galactic chemical evolution. By studying 3I Atlas's chemistry, scientists may one day piece together a map of the Milky Way's cometary fingerprint, identifying regions where specific types of interstellar objects are more likely to originate. Such knowledge would revolutionize our understanding of planetary system formation, revealing how the building blocks of life and the raw materials for planets are distributed across the galaxy. Yet perhaps the most enduring legacy of 3I Atlas lies inches its role as a bridge between humanity and the cosmos. Its discovery reminds us that we are not isolated inches the universe, but part of a grander tapestry woven by the same physical laws that govern the stars. Every observation of 3I Atlas is a dialogue across time and space, a conversation between civilizations separated by eons. When we analyze its nucleus's isotopic ratios or track its trajectory through the galaxy, we are engaging inches a form of cosmic archaeology, excavating the remnants of a universe that predates our existence. In this way, 3I Atlas is not merely a scientific curiosity, it is a symbol of our shared destiny, a reminder that the universe is a vast interconnected web of stories waiting to be told. As 3I Atlas departs the solar system, its legacy will endure inches the annals of astronomy and the collective imagination of humanity. Its journey has already reshaped our understanding of interstellar objects, challenging assumptions about their origins, compositions, and the mechanisms that propel them through space. Yet its significance extends beyond science. In the quiet moments between observations, when the comet is hidden behind the Sun and Mars is the only witness to its closest approach, we are left to ponder our place inches the cosmos. How many other travelers like 3I Atlas are currently crossing the void, unseen but present? How many more will arrive inches the future, bearing gifts from distant stars? The answers to these questions lie not only inches the data collected by telescopes, but inches the spirit of exploration that drives us to seek them. 3I Atlas is a reminder that the universe is vast, unpredictable, and full of wonder, a place where ancient comets whisper secrets of the past and future discoveries await. As we turn our gaze to the skies, we do so with the humility of explorers and the curiosity of children, ever eager to learn from the cosmos. And inches that pursuit, we find not just knowledge, but a deeper connection to the infinite. In the vast silent expanse of the cosmos, where time stretches into epochs beyond human comprehension, 3I Atlas drifts like a spectral envoy from the farthest reaches of the galaxy. Discovered on 1 July 2025 by the Atlas telescope inches Chile, this interstellar comet is more than a fleeting visitor to the solar system. It is a relic of antiquity, a fragment of a distant star system's birthright, now traversing the vacuum between suns. Its arrival stirs a profound question. What stories does it carry from the cosmic deep? As it hurtles through the inner solar system at 58 kilometers per second, a velocity so great it defies the gravitational bonds of its origin, 3I Atlas becomes a messenger, bearing fragments of alien chemistry and ancient history. Its hyperbolic trajectory, unshackled by the sun's pull, marks it as the third confirmed interstellar traveler after Oumuamua and Borisov. Yet its uniqueness lies inches its age, its composition, and the direction from which it came. To observe 3I Atlas is to witness a collision of scales. The intimate dance of ice and gas inches its coma, the grand sweep of its galactic journey, and the humbling realization that we are but observers inches a universe teeming with motion and memory. This comet is not merely a rock and ice adrift inches space. It is a time capsule, forged inches a stellar nursery billions of years ago, long before the sun ignited. Its nucleus shrouded inches a haze of carbon dioxide and water vapor, whispers of a home system where conditions differ from our own. The fact that it originates from the Milky Way's thick disk, a region dominated by ancient stars, suggests that 3I Atlas may predate the solar system itself, perhaps by 3 to 10 billion years. Such an object is a bridge between epochs, a connection between the primordial chaos of the early universe and the structured order of modern planetary systems. In its quiet passage, 3i Atlas compels us to reconsider our place in the cosmos. Are we alone in this vast shared heritage, or do we share a cosmic ancestry with countless other worlds scattered across the stars? To understand 3i Atlas is to unravel the threads of its journey. Its hyperbolic orbit, defined by a velocity that exceeds the escape speed of the solar system, confirms its interstellar origin. Unlike asteroids or comets born in our own backyard, 3i Atlas arrived uninvited, its path traced back to the direction of the galactic center. This origin point is significant. The thick disk of the Milky Way, where 3i Atlas is believed to have formed, is a region of older metal-poor stars. These stars, relics of the galaxy's youth, orbit a flattened, warped structure that extends above and below the galactic plane. The vertical velocity component of 3i Atlas, its motion perpendicular to the galactic plane, places it among this ancient population, suggesting it formed an environment where star formation was once rampant but has since waned. The comet's chemical signature further distinguishes it. Observations by the James Webb Space Telescope reveal an unusual richness in carbon dioxide, a molecule relatively uncommon in solar system comet. While water ice and carbon monoxide are present, they exist in proportions that hint at a different evolutionary path, one shaped by the unique conditions of its home system. The detection of cyanide gas and atomic nickel vapor, reminiscent of comets in our own neighborhood, underscores a paradox. Despite its alien origins, 3i Atlas shares familiar traits with the icy bodies of the Kuiper Belt and Oort cloud. This duality, both foreign and familiar, challenges assumptions about the homogeneity of planetary systems. If 3i Atlas's chemistry reflects the diversity of interstellar materials, then perhaps the building blocks of life or the precursors to life are not unique to Earth, but are instead woven into the fabric of the galaxy itself. The comet's activity, driven by solar heating, offers another layer of insight. As sunlight warms its nucleus, volatile compounds sublime it, releasing gas and dust to form a glowing coma. This process mirrors the behavior of comets in the solar system, yet the efficiency of 3i Atlas's outgassing suggests a different internal structure. Its nucleus, estimated to be less than 1 kilometer diameter, must be porous or contain fissures that allow rapid release of volatiles. Such characteristics imply a history of bombardment or tidal forces in its native system, shaping it into a fragile, reactive body. The fact that it remains active at a distance of 1.36 AU from the Sun, closer than Mars but farther than Earth, indicates a high concentration of easily sublimated ices, further distinguishing it from solar system comets. By studying 3i Atlas, scientists are not merely observing a passing phenomenon, they are decoding the legacy of a lost world. Its trajectory, chemistry, and activity serve as clues to the processes that govern the formation and evolution of planetary systems. The comet's hyperbolic excess velocity, for instance, provides critical data on the distribution of interstellar objects in the galaxy. If 3i Atlas is representative of a broader population, then the Milky Way may be a dynamic crucible of ejected material, with countless comets and asteroids drifting silently between stars. This perspective reframes our understanding of the cosmos. Rather than a static backdrop, the galaxy is a living, breathing entity, constantly recycling and redistributing its contents. The implications of 3i Atlas extend beyond astrophysics into the realm of existential reflection. Its existence challenges the notion of isolation in the universe, offering a tangible link between disparate stellar systems. Every atom in our bodies, every molecule in the oceans, may trace its lineage to the same cosmic forge that birthed 3i Atlas. The carbon in our DNA, the oxygen we breathe, the iron in our blood, all these elements were forged in the hearts of ancient stars, scattered into the void by supernovae, and later incorporated into planets, comets, and life itself. In this sense, 3i Atlas is not just an object from another system, it is a cousin in the family tree of matter, a reminder that the universe is a web of interconnected histories. Yet the deeper question remains: are we alone inches this shared heritage? The presence of organic molecules inches 3I at Alice. Cyanide, water, and complex carbon compounds raises tantalizing possibilities. These substances are the building blocks of life as we know it, and their abundance inches interstellar space suggests that the prerequisites for life are not exclusive to Earth. If 3I at Alice carries such molecules, could they have seeded other worlds during its journey? Or does its mere existence imply that the ingredients for life are ubiquitous, waiting for the right conditions to ignite? The answer may lie inches the next phase of exploration, analyzing the isotopic ratios of 3I at Alice's volatiles, comparing them to those found inches meteorites and comets from the solar system. Such studies could reveal whether interstellar objects share a common origin or represent a mosaic of diverse environments. Moreover, 3I Atlas's southern origin disrupts previous assumptions about the distribution of interstellar objects. Astronomers had predicted that most interstellar visitors would originate from the solar apex, the direction of the sun's motion through the galaxy, because the density of stars inches that region increases the likelihood of ejection events. However, 3I Atlas emerged from the opposite hemisphere, a rarity that hints at either an underappreciated asymmetry inches the galaxy, or a more abundant population of southern origin interstellar objects. If the latter is true, then the universe may be even more interconnected than we imagined, with material from one quadrant of the galaxy regularly traversing to another. This possibility reshapes our understanding of cosmic ecology. The galaxy is not a collection of isolated systems but a vast interwoven network, where the debris of one star system becomes the raw material for another. Perhaps the most profound implication of 3I Atlas is its age. If the comet is indeed 7 to 14 billion years old, it predates the solar system by billions of years, placing it inches an era when the Milky Way was young and star formation was rampant. In that distant past, collisions between protostars and planetary embryos would have been frequent, ejecting icy bodies like 3I Atlas into the galactic abyss. These objects, frozen inches time, now serve as time capsules, preserving the chemical and physical conditions of their birthplaces. By studying them, we gain a window into the early universe, a chance to piece together the history of star formation and planetary evolution. In this way, 3I Atlas is not merely a visitor. It is a teacher, offering lessons written inches ice and gas, encoded inches its trajectory and composition. As 3I Atlas recedes from the inner solar system, its story continues to unfold inches the minds of those who witnessed its brief apparition. By October 2025, it will have passed perihelion, its closest approach to the sun, and will disappear behind the glare of daylight, invisible to Earth-based observers. Yet its legacy will persist. The data gathered by telescopes on Earth and inches space, Hubble's images, the James Webb spectral analyses, the Very Large Telescope's detection of cyanide and nickel, will fuel decades of research. Scientists will model its trajectory with greater precision, refine estimates of its age, and search for other interstellar travelers that may have slipped past unnoticed. But beyond the science, 3I Atlas leaves an indelible mark on the human imagination. It is a reminder that the universe is not a void, but a dynamic, ever-changing tapestry. The same forces that sculpted 3I Atlas's icy nucleus and sent it careening through the cosmos also shape the planets, moons, and stars that surround us. In its journey, we see the echoes of ancient stars, the remnants of long-dead worlds, and the promise of futures yet to be written. As 3I Atlas vanishes from our skies, it carries with it the seeds of curiosity and wonder, urging us to look beyond the familiar and embrace the infinite. For inches the dance of matter and energy across the stars, we find not isolation, but kinship, a shared destiny written inches the language of the cosmos.